Hello, and welcome to Learn When You Sleep. Right now, as the world fades away around you, I want you to consider a mystery that most people will never even imagine. You are lying in the dark, perhaps ready for rest, but out there, in the vastness of the cosmos, there is a darkness far deeper than anything we know. Tonight, we are not just looking at the stars. We are looking for what lies between them. We are going to take a slow, deep journey into the hidden side of our universe. This is not a fast-paced adventure filled with loud facts. This is a journey that moves with the stillness of deep space itself. Imagine, for a moment, that everything you were taught about planets is only half of the story. We imagine planets as parts of a family, always circling a warm sun, always bathed in light. We think of Earth, Mars, and Jupiter as permanent residents of a solar system. But there are others, scattered through the galaxy, drifting through the eternal night between the stars. There are worlds that belong to nothing. These are the orphans of the cosmos, planets that were once part of a family, but were flung away into the void by forces so massive that not even the bond of a star could hold them. They travel alone. They carry no sun with them. They move through the interstellar dark in a silence so absolute that the word silence itself feels inadequate. We call them rogue planets. And tonight, we are going to travel with them, gently, until this thought becomes something you can rest inside. Why does the idea of a rogue planet feel so haunting, yet so deeply personal? It is an invitation to think about what it means to exist without a destination, to carry your own heat within you even when the cold outside is total. These wandering worlds are not just rock and ice. They are ancient giants, shaped by pressures we cannot imagine, moving through infinite space like a heartbeat in the dark. There is something in their situation that speaks to a quiet truth in the experience of being alive. The image of a world cut loose from its family, still warm inside, still carrying the memory of what it once was, is perhaps the most beautiful solitude in the universe. Tonight, we follow one of these wandering worlds. We will think about how it was thrown into the dark, what its silent surface looks like, and what secrets might stir in its hidden depths. Take a breath now. Let your shoulders drop. Let the weight of the day settle into the mattress beneath you. We are not going anywhere fast tonight. We are going somewhere quiet. We are heading into the dark between the stars, where something ancient and alone is still moving, still traveling through a universe so large that the word alone barely begins to describe it. And strangely, beautifully, that is exactly where we need to be. Before we can follow our wandering world, we must understand what it truly means to be a rogue. The word itself suggests something that has broken from the expected path. A rogue planet is a world in motion, moving through the galaxy without being bound to any star, without orbiting any center, without belonging to any system. The technical definition of a rogue planet is simple, but its reality is profound. It is a planetary mass object that does not orbit a star. It is massive enough to be a sphere, to have its own geology, its own layers of rock and ice, but it is not a star. It does not burn with nuclear fire. It only moves steadily through the interstellar space, following the slow, large-scale pull of the galaxy as a whole. For decades, scientists suspected these worlds existed, but they remained invisible, hidden in the shadows of the Milky Way. The logic was clear. If solar systems form in chaos, with planets smashing into each other and gravity pulling in every direction, it is inevitable that some worlds would be kicked out. Some would be ejected into the void before they could ever find a stable home. The galaxy, therefore, should be full of them. Invisible, frozen on the outside, but drifting in absolute silence. But finding a dark object in a dark universe is one of the greatest challenges in astronomy. Rogue planets emit no light. They do not wobble or transit a sun. They are ghosts. And yet, we found a way to see them. By using a technique called gravitational microlensing, we began to detect the impossible. We looked for the way these dark worlds bend the light of stars far behind them. Gravity curves space, and a rogue planet acts like a lens, magnifying a distant star for a brief moment as it passes by. When that brightening occurs without a star being present, it reveals the ghost. It reveals a world traveling alone. These detections were thrilling because they revealed a hidden truth about our galaxy. Early data suggested that rogue planets might be extraordinarily common. Some estimates now propose that there could be more rogue planets than there are stars in the Milky Way. Think about that for a moment as you drift closer to sleep. For every sun you see burning in the night sky, there might be several dark worlds moving silently in the spaces between them. The universe that looked so full of light is, in fact, even fuller of darkness. But this is not a cause for fear. It is a cause for a particular kind of quiet wonder. The universe is richer than we thought. It carries more history, more possibility, and more silent motion than the starlit sky suggests. Every night when you look up, you are only seeing the brightest layer of something that stretches deep and dark in every direction. And through that dark, right now, rogue planets are moving. They are the hidden residents of the cosmos, carrying their ancient histories into the next billion years. To think about them is to think about the hidden universe, the things that do not shine but still exist, still matter, and still move. This thought is deeply comforting. The universe holds more than we can see, and some of what it holds is beautiful in its solitude. To understand how a planet finds itself in this eternal dark, we have to go back to its birth. The story of a rogue planet begins in the same violent, beautiful way as any other world, within a churning cloud of gas and dust spiraling around a young star. Imagine the early days of a solar system, long before the planet was cast out. Gravity does not hurry. It accumulates matter grain by grain, building boulders, then mountains, then moons. But this process is far from peaceful. The early solar system was a place of extraordinary violence, where bodies the size of continents smashed into each other. In the struggle to find a stable orbit, the gravitational dance becomes a game of survival. In many systems, dozens of large worlds form, but only a few can stay. When two giant planets pass each other at regular intervals, they deliver small gravitational kicks. Like a child on a swing, these kicks add up. The orbit of a smaller planet begins to stretch, growing more and more extreme, until the path becomes chaotic. Eventually, the planet reaches a tipping point. It is not a collision or a fiery death, but something much more final. Ejection, a gravitational encounter so powerful that the planet is given enough speed to escape its solar system forever. From that moment on, the star it once called home begins to shrink. It becomes a bright point, then just another star, until finally, it is indistinguishable from the rest of the galaxy. The planet is no longer bound. It is free, but it is alone. And as it moves further away from the warmth, the long journey into the deep interstellar medium begins. This world is now a wanderer, and as it drifts, it carries the silent memory of everything it used to be. Dozens of them may have passed through or near our own solar system since it formed. Most left no trace we could detect. They simply moved through and continued on, silent and alone, carrying their ancient histories into the next billion years. To think about rogue planets is to think about the hidden universe. The universe of dark things that do not shine, but still exist, still matter, still move, still carry, perhaps, the ingredients of something extraordinary. And that thought, as quiet and as dark as it is also somehow deeply comforting. The universe is richer than it looks. It holds more than we can see. And some of what it holds is moving right now through the dark between the stars, ancient and alone and beautiful in its solitude. To understand how a planet can be thrown into the dark, we first need to understand how planets come to exist at all. And that story, the story of planetary birth, is one of the most violent and beautiful processes in the universe. It begins not with calm and order, but with a vast churning cloud of gas and dust, slowly pulled inward by gravity, spinning faster and faster as it collapses, until a star ignites at the center and the remaining material flattens into a disk. Picture it slowly, if you can. Long before our solar system existed, there was a region of the galaxy where gas and dust had gathered, drawn together by the gentle but persistent pull of gravity. This was not a dramatic event at first. It was gradual, patient, a slow thickening of matter in a particular region of space, the kind of process that takes millions of years to develop any visible structure. But gravity does not hurry. It simply accumulates, and what begins as a faint concentration eventually becomes a denser knot, and that knot begins to pull in more material, and the material begins to spiral inward, and as it spirals, it spins. The spinning is important. As the cloud of gas and dust collapses under its own gravity, the slight rotational motion it already had begins to accelerate, the same way a figure skater spins faster when they pull their arms inward. The collapsing cloud spins faster and faster, and instead of falling all the way into a single point, most of the material spreads out into a disk. A protoplanetary disk, flat and vast, and swirling around the infant star that is forming at its center. At the center, the pressure and heat have become so intense that hydrogen atoms begin to fuse. The star ignites, and around it, the disk of gas and dust begins its own extraordinary process of organization. Within the disk, particles collide. Dust grains stick together when they meet. Small clusters form. Small clusters collide with other small clusters, and sometimes they stick and sometimes they shatter. But over millions of years, the ones that stick accumulate into larger and larger bodies. These are called planetesimals, small, irregular, rocky, or icy chunks, ranging in size from boulders to mountains to small moons. They are the raw material of planets. They orbit the young star within the disk, crossing each other's paths, colliding, merging, growing. The process is not peaceful. The early solar system was a place of extraordinary violence. Impacts were constant. Bodies the size of cities smashed into bodies the size of continents. Entire forming worlds were destroyed, and their materials scattered back into the disk or accumulated by larger neighbors. The biggest and most well-positioned of the planetesimals grew fastest because their larger gravity pulled in more material, which made them larger still, which made their gravity stronger still. A runaway process of growth, a gravitational snowball rolling through the disk, gathering everything it encountered. Within a few million years, the disk had organized itself into a smaller number of larger bodies. Gas giants had accumulated so much material that they pulled in enormous envelopes of hydrogen and helium directly from the disk. Rocky worlds had formed in the inner regions, where the heat from the young star had driven off the lighter gases. And the disk itself was thinning, its material being consumed by the forming planets, blown away by the stellar wind, or gradually settling into stable orbits. In our own solar system, this process produced 8 planets that survived. But in many solar systems, the process produces dozens of large protoplanets before the final configuration settles. And the settling process, the gravitational dance by which all of these forming worlds find their final orbits, is where things can go very wrong for some of them. Because the disk is not a peaceful place, even after the first generation of planets has formed. The planets interact with each other gravitationally. They perturb each other's orbits. They exchange angular momentum in complex ways. And in some systems, particularly in systems where the planets are numerous, or where the planets are massive, or where the early configuration happens to be unstable, those gravitational interactions can produce something catastrophic. A resonance. A gravitational resonance is what happens when 2 orbiting bodies pass each other at regular intervals, and each pass delivers a small gravitational kick that, over thousands or millions of repetitions, adds up to something enormous. Think of pushing a child on a swing. Each individual push is small, but if you time the pushes correctly, if you push each time the swing comes back to you, the amplitude grows and grows until eventually the swing is going very high indeed. In a solar system, gravitational resonances between planets can do the same thing. They can amplify small perturbations into large ones. They can take a planet that was in a stable orbit and, over millions of years, push that orbit into one that is more and more elliptical, more and more extreme, until finally the planet's path through the solar system becomes chaotic, crossing the orbits of other planets, coming dangerously close to the giant worlds, and ultimately being flung away. It is a slow process by human standards. It unfolds over millions and sometimes hundreds of millions of years, but it is relentless. And when it reaches its conclusion, the outcome for the unlucky planet is absolute. Not a collision, not absorption, not even the mercy of falling into the star. Simply ejection, a gravitational encounter so close and so powerful that the planet is given a velocity greater than the escape velocity of the entire solar system. And from that moment forward, it travels alone. The star it was formed around, the star that warmed its early surface, the star whose light it once received, recedes. Slowly at first, then faster, then it becomes a bright point among many points, then a slightly brighter star among many stars. And then, as the centuries and millennia accumulate, it becomes indistinguishable from all the other stars in the night sky of a world that no longer has a sun. Until finally, even that is gone. The stars of the home solar system are too far away to distinguish individually. The sky becomes just the sky, and the planet is alone, in the dark, moving through the galaxy at whatever velocity the gravitational encounter gave it. This is how a rogue planet is born. Not in a dramatic explosion, not in a collision, not in a fiery death, but in a long, slow process of gravitational exclusion, the result of a solar system that was simply not quite stable enough to hold all of its members. The planet did nothing wrong. It formed as it should have formed. It moved as it should have moved. But the mathematics of gravitational interaction played out over millions of years, simply did not permit it to stay. And so it left. Or rather, it was pushed, gently, and then with enormous force, into the dark. There is a moment in the life of what will become a rogue planet that we might think of as the moment of departure. Not a clean and ceremonial leave-taking, not a farewell with any dignity attached to it, but a moment of gravitational violence so extreme that a world is simply torn from its place in the solar family and sent spinning into the interstellar void. If you could watch it from a safe distance, over a compressed timescale, it might look almost graceful. A long elliptical path, then a closer ellipse, then closer still, until one pass near a giant planet provides the final push. And then the trajectory opens up, no longer a closed orbit looping back to the sun, but a hyperbolic arc that curves away and never curves back. Let us stay with that moment for a while. Imagine a world, perhaps something like our own Earth in size, though its history has been different. It formed in the outer reaches of a young solar system, a system with several large gas giants whose orbits were slowly shifting under the influence of their mutual gravity. For hundreds of millions of years, this planet moved along its orbit without trouble. Its surface was cold, far from its star, but it had an atmosphere of some kind, thick and dense with gases that had accumulated during its formation. It had moons, perhaps 2 or 3 small ones, captured from the swarm of planetesimals in the outer disk. It had geology, a young active interior still warm from the heat of formation, still generating volcanic activity, still shifting its crust in slow geological rhythms. It was, in every sense that the word can apply to a lifeless world, alive. But in the giant planet neighborhood, something had been building for millions of years. 2 of the large gas giants had drifted into a gravitational resonance, each orbit of one coinciding at regular intervals with an orbit of the other, and every coincidence delivered a small gravitational tug, not enough to feel catastrophically on any single pass, but accumulating, building, pushing the inner gas giant's orbit slowly outward in a great spiral of increasing eccentricity. And as the giant's orbit grew more elliptical, it began to cross new regions of the solar system, regions where other planets moved. The first close pass between the wandering giant and our planet was not the final one. It was not even particularly dramatic by cosmic standards. The giant swept past at a distance of several million kilometers, and the planet felt the encounter as a change in its orbital parameters. Its path stretched slightly. Its year grew slightly longer. Its orbit became slightly more elliptical. Nothing catastrophic. Not yet. But the second close pass was closer. The slight change in orbit that the first encounter produced meant that the planet arrived at a particular point in its orbit at a slightly different time. And that slight difference in timing meant the second encounter with the giant was more nearly head-on, the gravitational kick more precisely aligned with the planet's motion. The orbit stretched further. The year grew longer still. The planet was now on an orbit that swung far out into the cold reaches of the solar system before looping back in toward the warmer regions. An unstable orbit, an orbit that was already crossing the paths of other worlds. The final encounter came after several more orbital periods. It was closer than any before it. The giant planet loomed in the sky of our wandering world, its disk filling an area of sky that no moon had ever filled before. The gravitational tides were enormous, stretching the planet's crust, raising bulges in what liquid existed on the surface, triggering earthquakes in the deeper rock. It was not a collision. The 2 worlds did not touch. But the gravitational exchange at this range was enough to do something that could not be undone. The planet's velocity, relative to the Sun, exceeded escape velocity. In the language of orbital mechanics, its trajectory changed from a closed ellipse to an open hyperbola. In the language of experience, if there were experience on this world, the Sun suddenly began to shrink. Not the way it shrinks during the outward leg of an elliptical orbit, growing dimmer before the planet loops back. This time, it simply kept shrinking. There was no return leg. The orbit did not loop. It opened, and the planet moved away from the Sun, and the Sun grew dim, and the years passed, and the centuries, and the light continued to fade. The moons were another story. 2 of the 3 small moons that had orbited this planet were lost in the chaos of the final encounter. The gravitational interaction with the giant was enough to perturb their orbits beyond recovery. One was captured by the giant. One was flung onto a collision course with the Sun, a long, slow spiral inward that would take millions of years to complete, long after its parent world had vanished into the dark. Only the innermost moon survived, close enough to the planet to remain gravitationally bound through the chaos, close enough to follow its parent world into the darkness. So the rogue planet moved outward, with one small moon still circling it, into the void. The Sun, still visible, was now a star among stars, brighter than the others, but no longer special in the way a sun is special, no longer the warm center of a familiar sky. The other planets of the solar system, if they were visible at all, were just points of light moving slowly against the background. The planet's atmosphere, which had been held by the warmth of the Sun in a particular chemical balance, began to change. The temperatures dropped. The gases began to freeze, layer by layer, falling as snow onto a surface that grew colder with every passing century. And the stars, all of them now, receded. Not quickly. Nothing in this story happens quickly. But with the absolute inevitability of physics, the solar system became just one region of a sky full of stars, and then a slightly brighter region, and then simply one direction among many. The planet's sense of home, if we imagine something like sense, dissolved. There was no home direction anymore. No warmer quarter of the sky. No brighter star to navigate by. Only the even wash of starlight from the galaxy, and the planet moving through it, following the slow gravitational curves of the Milky Way rather than the tight elliptical orbit of a solar system. This is the moment of departure. Not dramatic, not even particularly visible to anyone watching from far away. A planet crosses a threshold from bound to unbound and continues in the direction it was already going, and the solar system shrinks behind it, and the dark expands ahead of it, and the journey, the long solitary journey that may last for billions of years, begins. There is something in this moment that resists the word catastrophe, even though by any ordinary definition, losing your sun is a catastrophe, because the planet simply continues. It does not stop. It does not collapse. It does not cease to be a world. It carries everything it was, everything it accumulated in its hundreds of millions of years of formation and early life, everything its interior holds, into the dark. It has changed irreversibly, but it is not ended. It is only alone. And alone, it moves on. There is a period in the earliest stage of a rogue planet's journey that we might think of as the long twilight. Not the dramatic instant of ejection, and not yet the deep and total darkness of true interstellar space, but the intermediate stage, the centuries and millennia during which the sun is still visible, still present in the sky, still casting some faint light on the surface of the retreating world, but growing dimmer with every passing year. This is a period of transition, and in some ways it is the most evocative stage of all, because it is the stage at which the loss is most visible, the stage at which the departure is still recent enough to be felt. In the very early years of the ejection, the sun would still be the brightest object in the sky, far brighter than any other star, a point of light that stands apart from all the others, not because it fills any portion of the sky in the way it does from Earth, but because its magnitude is still overwhelming compared to the distant stars of the galaxy. The planet would receive some warmth from this retreating sun. Not much. It was always far from the inner solar system. But something. A faint warming of the uppermost layers of the atmosphere. A slight slowing of the deep freeze that was already beginning. But the years pass, and each year, the sun is a little dimmer. After 10,000 years, the sun is still the brightest star, but it no longer stands apart in the way it did. It has joined the company of the very brightest stars in the sky, the class of objects that are simply bright points rather than overwhelming lights. The planet receives perhaps a 10,000th of the sunlight it received at the moment of ejection. Its atmosphere, which has been losing heat to space continuously, has dropped in temperature by hundreds of degrees. The first layers of atmospheric gas have frozen out. Nitrogen snow falls on the surface. Carbon dioxide, which was once part of a thick greenhouse atmosphere trapping what little heat the planet received, has frozen solid, blanketing the rocks in a white crust of dry ice. The sky, during these early millennia, would have been something extraordinary to behold. Not the familiar sky of a world with seasons and a daily cycle, because there is no daily cycle anymore. Without a star to rise and set, there is no day and night in the ordinary sense. The planet rotates, yes. It still spins on its axis. And as it spins, the galaxy wheels overhead, the river of stars that is the Milky Way sweeping across the sky in great arcs. But there is no sunrise. There is no sunset. There is only the constant presence of the stars, wheeling and returning, with the sun among them, growing dimmer year by year, decade by decade. Think about what that sky would look like. From the surface of this cold and darkening world, you would see more stars than are visible from any location on Earth, because there would be no atmosphere thick enough to scatter light, no moisture to blur the edges of things. The stars would be sharp, brilliant points, absolutely unmoving in any individual observation, but sweeping slowly overhead as the planet rotated. The Milky Way would be a river of light so bright and so detailed that it would cast faint shadows on the frozen surface beneath. The galaxy would not look the way it looks from Earth, a faint haze in dark sky country. It would look like something structural, something architectural, a great band of concentrated light with dark lanes running through it and bright clusters scattered along its length. And somewhere in that sky, growing smaller each year, would be the sun. After 100,000 years, the sun is no longer distinguishable from the other bright stars. It has faded to a point that could be confused with several dozen other stars of similar apparent brightness. If you did not know exactly where to look, you might not find it. The planet is now so far from the inner solar system that it would take light nearly a year to travel the distance between them. The warmth from that distant star is now effectively zero. What was once a solar system is now just a region of space where a particular collection of planets continues to orbit a particular star in a corner of the galaxy that this rogue world has already left far behind. The atmosphere of the planet, during this period, is undergoing a transformation that is final and total. Each gas has its own freezing point, and as the temperature drops below each threshold in turn, that gas stops being part of the atmosphere and starts being part of the surface. Water vapor, which might have existed in trace amounts even in the cold outer reaches of the original solar system, froze long ago. Carbon dioxide froze in the early centuries after ejection. Now the heavier gases are beginning to follow. Nitrogen, the most abundant atmospheric component of an Earth-like world, has a freezing point of nearly 200 degrees below zero on the Celsius scale, and the temperature at the surface is approaching that threshold. When the nitrogen freezes, the last atmosphere falls. It does not happen all at once. It is a gradual process, years and decades of slowly thickening frost, of atmospheric pressure slowly dropping, of the already thin air becoming thinner, until finally there is no longer enough gas to constitute an atmosphere in any meaningful sense. What remains is a surface layer of nitrogen frost covering the older carbon dioxide and water ice beneath, and above it, essentially nothing. No weather, no wind, no sound of any kind, because sound requires a medium to travel through, and there is no medium left. The silence that follows is complete. In all of human experience, in all of the silence we have ever imagined or encountered, there is nothing equivalent to the silence of a world that has lost its atmosphere. Because every silence on Earth is still threaded with sound if you listen carefully enough. The movement of air, the distant rumble of geological processes. Even in the quietest places, the air itself is vibrating slightly, carrying the memory of sounds from far away. On the surface of a rogue planet that has lost its atmosphere, there is nothing, no medium, no propagation. If something fell onto the surface, a meteor, a shard of rock, it would strike without making any sound. The impact would send vibrations through the rock, and those vibrations would propagate through the solid body of the world, but in the air above, nothing. It is a silence that is not empty, but absolute. The difference matters. An empty silence is the absence of sound in a space where sound could exist. An absolute silence is a condition in which the very possibility of sound has been removed. This world, in the darkness, falling deeper into the cold of interstellar space, has reached the condition of absolute silence. And yet, underneath that frozen surface, something continues. The interior of the planet, the deep rock and the iron core and the layers of compressed material in between, retains heat from two sources. From the original heat of formation, the energy of all those impacts during the solar system's early violent period, still slowly leaking outward through the rock, and from the decay of radioactive elements, uranium and thorium and potassium and others, which release energy as they break down, energy that has been heating the interior of the planet since before it even formed. Deep beneath the frozen surface, the rock is warm. Not warm the way a room is warm. Warm the way a geological deep structure is warm. Hundreds of degrees in the deepest regions. Warm enough, perhaps, to maintain something remarkable. Warm enough in certain layers at certain depths to keep water liquid. But we will reach that in time. For now, let us stay with the surface. The frozen, silent, dark surface of a world that has been traveling through the galaxy for hundreds of thousands of years. The stars will overhead in their slow arcs. The Milky Way is a constant presence, the brightest and most complex object in a sky full of brilliant points. The sun, that star, is now so far away that finding it requires knowing exactly which star to look for among thousands of candidates. It is there, but it is not special anymore. It is just a star. And the planet moves on. Through the dark, through the cold, through the absolute silence of interstellar space. Moving steadily, following the gentle gravitational curves of the galaxy, passing through regions of the Milky Way that its original solar system never visited, moving toward no destination in particular. Just moving, as physics requires it to move. As the momentum of that original ejection, combined with the gravity of the galaxy, keeps it moving. The first darkness has fully arrived, and it will last for a very long time. There is a question that arrives naturally when we think about a rogue planet moving through the dark, and it is this. What does the sky look like from the surface of a world that has no sun? It seems like a simple question, but the more you sit with it, the more it opens into something unexpectedly rich. Because the sky of a starless world is not simply dark. It is not simply the absence of a sun. It is something entirely its own, a sky unlike any sky that has ever been observed by human eyes, a sky that is in some ways more beautiful, more detailed, more full of structure than anything we see above us on Earth. Let us go there together, slowly. Imagine you are standing on the surface of this rogue world. The ground beneath your feet is frozen. Frozen so completely and for so long that the ice is not soft or powdery in the way of a recent snowfall, but hard as stone, compressed by its own weight and by the slow creep of geological time. The surface is flat in some places, ridged and fractured in others, where ancient geological activity has pushed up formations that have since been locked in place by the cold, preserved as perfectly as a fossil in amber. There is no wind. There has not been wind for hundreds of millions of years. The formations are exactly as they were formed. Nothing has smoothed them. Nothing has eroded them. They stand sharp and unchanging in the dark. And the sky above all of this is astonishing. The first thing you would notice is the stars. Not a few stars, not hundreds of stars, not even the few thousand that are visible from Earth on the clearest night. The stars from the surface of a rogue planet, in the absence of any atmosphere to scatter or absorb their light, would number in the hundreds of thousands with the naked eye. Every star that is too faint for our atmosphere to transmit would be visible here. The sky would be thick with them, a density of light that begins to look less like a scattering of individual points and more like a texture, a granular luminosity that covers the entire dome of the sky. And it would not be uniform. The sky of a starless world would have structure that we on Earth can barely guess at. The Milky Way, which appears to us as a faint hazy band across the sky on the clearest nights, would reveal itself here as something architectural. A vast river of light, yes, but a river with internal detail, with bright clusters standing out like cities along a coastline, with dark rifts running through it where clouds of dust absorb the light of the stars behind them, with regions of glowing nebulosity where young stars are illuminating the gas that surrounds them, casting a faint colored light across the sky. The galaxy would not be a suggestion, it would be a presence, a structure so detailed and so brilliant that it would dominate the sky the way the sun dominates ours. But unlike the sun, it would not be blinding. You could look at the Milky Way for as long as you wished, taking in the details, following the dark lanes, locating the bright knots of star clusters, noticing the subtle gradation from the bright center of the galaxy to the thinner edges. It would be the most complex and beautiful thing in the sky, and it would be there every moment of every rotation, never setting, never rising, just wheeling slowly overhead as the planet turns. The other galaxies would be visible too. Not just Andromeda as a faint smudge, the way it appears on Earth, but as a resolved shape, an elongated brightness with internal structure, a disk seen at an angle with the brighter core at its center and the fainter arms extending outward. Other nearby galaxies, the Triangulum Galaxy, the clouds of the Magellanic Stream, if this world is in the right part of the galaxy, would appear as patches of soft light scattered across the sky. The deep sky, the realm beyond our galaxy, would be visible in ways that no human eye has ever seen it, with enough stars removed from the foreground by the absence of atmosphere that even some of the background galaxies would catch the eye as faint patches of structured light. And then there is the color. Stars are not all the same color. We know this intellectually, but from the surface of the Earth, the colors of stars are difficult to see because our atmosphere and our eyes, adapted to the brighter light of day, do not register star colors well in the dark. But from the surface of a rogue planet, with no atmosphere and a sky dark enough to make the stars the brightest things in existence, the colors would be unmistakable. Blue-white stars, the young and intensely hot ones, burning with a light that is genuinely blue. Yellow stars like our sun, steady and warm colored in the middle of the spectrum. Orange and red stars, the older and cooler ones, glowing with a deep ruddy light that is almost gentle. The sky would not be a monochrome field of white points. It would be a tapestry of colors, subtle but real, painted across the dark in a palette that no artist has ever had access to. There would also be brightness variation over time, though slow. Some stars are variable, pulsing in brightness over periods of days or weeks or months. From a rogue planet with no atmosphere and no competition from a sun, these variations would be directly observable. A particular star might brighten noticeably over the course of a week, then slowly dim, then brighten again, marking out its cycle with the regularity of a cosmic clock. Others would flare unpredictably, a distant stellar eruption brightening a single point of light for hours before it fades. And occasionally, over the very long timescales of the planet's journey, a star would appear that was not there before. A supernova, a dying star in a distant system releasing more energy in a moment than it released in its entire previous lifetime, briefly brightening to a point where it would cast faint shadows on the frozen surface below. These supernovae would be the closest thing this world has to an event, to a punctuation in the long silence of its journey. A new star appearing in the sky, too bright to be an ordinary star, casting genuine light on the frozen landscape, illuminating the sharp ridges and the flat plains of ice with a cold and colorless light that lasts for days or weeks before slowly fading. And then the sky returns to its ordinary state, brilliant and detailed and utterly still, and the rogue planet continues on its way. What would be absent from this sky is almost as interesting as what is present. There would be no sun, of course, no daily cycle of light and dark, no blue sky, because blue sky requires an atmosphere to scatter sunlight, and there is neither atmosphere nor sunlight. No clouds, no weather of any kind in the sky above, no aurora, because aurora require both a magnetic interaction with a solar wind and an atmosphere to fluoresce. The sun that once drove this planet's space weather is now too far away to send any meaningful solar wind, and even if it did, there is no atmosphere to interact with. The sky is pure and unchanging. It is the sky of deep space, seen from a surface rather than from a spacecraft. It is the most honest sky possible, unfiltered, unobstructed, showing exactly what the universe looks like when nothing stands between the eye and the cosmos. And it is beautiful in a way that is very different from the beauty of an earthly sky. It does not change with the weather. It does not glow at sunrise or blaze at sunset. It does not carry the drama of storms or the softness of clouds. It simply is. Constant, detailed, overwhelming in its richness. The same sky tonight as it was 1,000,000 years ago, and as it will be 1,000,000 years from now. A sky that has been looking down on this frozen world since the day it was ejected, watching with the patience of the cosmos, asking nothing, offering nothing but light, cold and ancient and beautiful. This is the sky of a starless world. And if you stood on its surface and looked up, you would see not emptiness, but the most complete view of the universe that any surface has ever offered. You would see the galaxy as it truly is. You would see the cosmos without interruption. And you would understand, in a way that no amount of reading can fully convey, that darkness is not the absence of beauty. It is its own kind of beauty, the kind that requires no sun to exist. We have looked up from the surface of this rogue world, and we have seen the sky. Now let us look down. Let us think about what the surface itself is like, what it is made of, how it came to be this way, and what it holds in its frozen stillness. Because the surface of a rogue planet, while it looks at first like nothing more than a featureless expanse of ice and rock, turns out to be a kind of archive, a record of everything this world has been, preserved in the cold with a fidelity that no warmer world could match. The surface temperature of a rogue planet, once it has fully lost its atmosphere and traveled far from any star, falls to something close to the temperature of the surrounding interstellar medium. That temperature, in the empty space between the stars, is extraordinarily cold. About 270 degrees below zero on the Celsius scale, only a few degrees above what physicists call absolute zero, the theoretical minimum temperature at which all thermal motion ceases. This is not the cold of a winter night, or even the cold of the poles of Mars. This is a cold so profound that most of the substances we encounter in daily life would not merely freeze solid, but would become rigid and brittle beyond anything our intuitions can easily model. Iron would not be particularly different. Iron freezes at temperatures well above this, and at the temperatures of interstellar space, it would simply be a cold, hard metal, the same iron that has been in the planet's core since its formation. But water ice, which we think of as a cold substance, would be harder at these temperatures than granite. It would not be possible to scratch it easily. It would ring rather than crunch if struck, more like glass or ceramic than the ice of a skating rink. Carbon dioxide ice would behave similarly, locked into a crystalline structure so rigid that it would seem more mineral than frozen gas to any observer who encountered it. The surface of this world, under the starlight, would look like a landscape of stone. And it would have a landscape. That is perhaps the most surprising thing. When we imagine a frozen world, we tend to imagine flatness, a featureless plain of ice stretching to the horizon. But geology does not produce featureless plains. Geology produces mountains, valleys, ridges, cliffs, craters, plains, and all the other structures that arise when rock is under pressure and in motion. And this world, even now, long after its active geological period ended, retains the record of everything its geology produced when it was still warm enough to be active. In the early period after ejection, when the interior was still warm enough to drive geological processes, the surface was not static. Volcanoes erupted, though their eruptions were more subdued than on Earth because the planet was already cooling rapidly. The geological activity pushed up mountain ranges in some regions, opened rifts in others, produced lava flows that spread across the surface and then froze in place. Impacts continued, too. Meteors and comets struck the surface in the early period of the journey, leaving craters that are perfectly preserved because there is no wind to erode them, no water to soften their edges, no geological activity to slowly erase them. A crater made 1 billion years ago on this world looks exactly as it did the day it was formed. The surface is therefore a museum. Every geological event in this world's history is recorded in its topography because nothing has been erased. The mountain range pushed up by tectonic forces 3 billion years ago still stands at the height it reached when it was formed, its peaks as sharp as the day they were shaped. The lava flow that spread across the northern plain 2 billion years ago is still there, still textured with the ripples and folds that formed as it cooled, still bearing the small collapsed pits where gas bubbles rose through the cooling rock. The craters, hundreds of them, from micrometeorites to large impacts, are all present, overlapping where the timing of their formation was close, pristine where they formed in isolation. This preservation has something deeply peaceful about it. On a world like Earth, the surface is constantly being remade. Rain erodes rock, wind smooths ridges. Tectonic activity buries old structures under new ones. The oceans slowly dissolve the past and deposit new sediment. Earth's surface is one of the most dynamic environments in the solar system, constantly overriding its own history, keeping only fragments of its past in deep geological records that require enormous effort to read. The rogue planet is the opposite of this. Its surface is as still as a photograph, as preserved as a fossil. Every detail of its geological history is on display, layered one upon another in a stratigraphy of events that stretches back to the planet's formation. To walk across, it would be to walk through time, each step covering ground that was shaped by forces that operated millions or billions of years ago, each ridgeline a remnant of an ancient tectonics, each crater a record of an ancient impact. The ice itself has layers. In the earliest years of the planet's ejection, as the atmosphere froze out layer by layer, each gas fell at a different rate and formed a distinct stratum in the surface ice. First the water ice, then the carbon dioxide ice, then, over longer timescales as the temperature continued to drop, the nitrogen and the argon and the other atmospheric gases, each forming its own layer, each layer preserving within it any particles or chemicals that were present in the atmosphere at the time of freezing. These layers are not large. They are thin, some of them only millimeters thick, but they are distinct, and if you could examine them in a cross-section, they would tell the story of the atmosphere's final days in extraordinary detail. The chemical composition of each layer, the isotopic ratios of the elements within it, the presence or absence of particular molecules, all of these would be readable as a history of an atmosphere that once existed and is now gone, frozen into the ground of the world that once breathed it. There is also cosmic material in the surface layers. As the rogue planet travels through the interstellar medium, it sweeps up particles. The interstellar medium is not empty. It contains gas atoms, mostly hydrogen, dust grains, complex organic molecules that form in the cold reaches of molecular clouds, cosmic rays that are actually not rays at all, but energetic particles moving at nearly the speed of light. Some of these particles are captured by the planet's gravity and settle onto the surface. Over billions of years of travel, this accumulation is not trivial. A thin but chemically rich layer of interstellar material has been deposited on top of the original frozen atmosphere. This layer would be a record of everywhere the planet has been. Different regions of the galaxy have slightly different chemical signatures, different ratios of elements, different types of dust grains, different complex molecules. As the planet passes through one region and then another, the material it sweeps up changes slightly, and each change is preserved in the surface layer at the time of passage. The surface of a rogue planet is, in this sense, a diary of its journey, a chemical record of the regions of the galaxy it has traversed, written in the accumulated dust of interstellar space. Standing on this surface in the starlight, looking out across the frozen landscape, you would see a world that is utterly still and utterly ancient. The starlight is dim by day standards, but not by the standards of a sky full of hundreds of thousands of stars. It would be enough to see the nearby ridges and the craters and the far horizon where the curve of the world brings the ice fields to an edge against the star-filled sky. It is a landscape that is, in its own way, not desolate. Desolation implies that something was expected here and is absent, but nothing was ever expected on this surface. This world was never hospitable, never warm enough for liquid water on its surface, never touched by the complexities that life requires to begin on an exposed surface. It is simply what it is, an ancient, preserved, frozen landscape, moving through the galaxy in silence, carrying its record of 4 billion years of history in every ridge and crater and chemical layer. Still, utterly still, and somehow, in that stillness, complete. Everything we have described so far about the rogue planet exists at the surface, in the cold and the dark and the silence. But the surface is only the beginning of the story. It is only the outermost layer of something far more complex and far warmer within. Because while the surface of this world has been frozen for hundreds of millions of years, while the temperature just a few meters down is not appreciably different from the temperature at the top, something changes as you go deeper. Something changes in a way that is, when you think about it, one of the most remarkable facts about the physical nature of planets. The interior of a planet is warm. Not mildly warm, not lukewarm. Genuinely, profoundly warm, in ways that have nothing to do with the sun, nothing to do with any external source of energy, but everything to do with the internal nature of the planet itself. And that warmth, sealed inside this frozen world like a fire inside a block of ice, is the most important thing about a rogue planet. It is the thing that makes these worlds interesting. It is the thing that makes them, against all expectation, potentially alive. There are two main sources of this interior heat. The first is the oldest. When the planet formed billions of years ago, it did so through the accumulation of smaller bodies, the violent collisions and mergers of planetesimals that we described earlier. Each of those collisions released energy. The kinetic energy of two objects slamming together at orbital velocities is converted, upon impact, into heat, and the planet that formed from those collisions absorbed all of that heat into its interior. The energy was enormous. The total kinetic energy of the planetary formation process, summed across the millions of collisions that built a world the size of the Earth, is equivalent to the energy released by the sun over millions of years. That energy did not disappear. Energy does not disappear. It became heat, and the heat was trapped inside the forming planet by the rock and metal above it. The young planet was essentially molten throughout, a ball of liquid rock and metal, glowing with the energy of its own formation. Over time, the surface cooled and formed a crust. The interior cooled more slowly, because rock is a poor conductor of heat. And billions of years later, even now, after billions of years of cooling, a significant fraction of that original formation heat remains. Deep inside the rogue planet, at depths of hundreds of kilometers, the rock is still warm from collisions that happened before the solar system had finished forming. This is itself a remarkable thought. The warmth at the center of a planet is partly a memory stored in the rock of the violence of formation, of the billions of years that were required to build a world. It is ancient heat from a time before the planet had a surface, before it had an atmosphere, before it was anything recognizable as a world. That heat is still there, slowly leaking outward, slowly warming the layers above it, reaching, in diminished form, toward the surface. The second source of interior heat is more continuous and in some ways more interesting. Scattered throughout the rock of every planet that forms from the material of a solar system are radioactive elements. Uranium, thorium, potassium-40, and several others in smaller quantities. These elements are unstable. Their atomic nuclei decay over time, each decay releasing a small amount of energy in the form of heat. The half-lives of these elements are measured in billions of years, which means that even now, billions of years after the planet formed, they are still decaying, still releasing heat, still contributing to the warmth of the interior. The total power generated by radioactive decay inside a planet the size of Earth is not enormous by stellar standards. It is measured in tens of terawatts, a number that sounds large in human terms, but is small compared to the energy of the sun. But it is continuous. It does not run out quickly. It simply persists year after year, decade after decade, century after century, slowly declining as the radioactive elements are used up, but declining so slowly that on the timescale of a planet's lifetime, the variation is modest. For a rogue planet moving through interstellar space, this radioactive heat generation is everything. There is no other energy source. No sunlight, no tidal heating from a nearby large body, no internal processes driven by external forces, only the slow decay of radioactive elements, distributed throughout the rock, generating heat that has nowhere to go but slowly upward through the poor thermal conductor of the planetary interior. And because there is nowhere for the heat to go quickly, because the rock conducts heat poorly and the cold surface acts as a barrier, the heat accumulates in the deep interior. The temperature profile of a rogue planet is therefore extraordinary. At the surface, temperatures are close to absolute zero, just a few degrees above the background temperature of the interstellar medium. A meter or two down, the temperature is essentially the same. But as you descend into the planet, through the kilometers of frozen rock and ice that make up the outer layers, the temperature begins to rise. Slowly at first, then more steeply as you reach the depths where the radioactive heating is concentrated and where the insulating rock prevents the heat from escaping easily. At depths of several tens of kilometers, the temperature might be above the freezing point of water. And at greater depths, in the regions where the rock is under enormous pressure from the weight of everything above it, the temperature might be hundreds of degrees above zero. The rock at these depths is not liquid, because the pressure keeps it solid, but it is warm. Warm enough to be geologically active in a slow and quiet way. Warm enough to drive the very gradual convection of hot rock rising and cooler rock sinking, a process that is glacially slow but never entirely stopped. And somewhere in that temperature gradient, somewhere between the frozen surface and the hot, deep interior, there is a zone where the temperature passes through the range where water is liquid. Between 0 degrees and 100 degrees Celsius, the freezing point and the boiling point. In that zone, if there is water present, and in a planet that formed from the material of a solar system, there is almost certainly water present. That water would be liquid. It would not be on the surface, where it would freeze instantly. It would not be in the deep interior, where the pressure and temperature would turn it to steam or to exotic high-pressure ice phases. It would be in between, in a layer, a hidden layer, an ocean that has never seen sunlight, that has been sealed in darkness since the moment the surface froze, that has been circulating in the deep rock for hundreds of millions of years, kept liquid by the warmth from below and insulated from the cold by the kilometers of ice and frozen rock above. This is the warm heart of the rogue planet. Not the core of iron and nickel at the very center, though that too is warm, but the intermediate zone, the hidden layer where physics conspires to maintain conditions that are, by any measure, extraordinary. A layer of liquid water in the frozen darkness. A layer of warmth inside a world that looks, from the outside, like nothing but cold. The discovery, or rather the theoretical prediction, that such layers might exist inside rogue planets is one of the more surprising results of planetary science in recent decades. It required thinking carefully about energy budgets, about the thermal conductivity of rock and ice, about the freezing points of water under pressure, about the rate of radioactive decay. And when all of those calculations are done, the conclusion is compelling. Many rogue planets, perhaps most of them, should carry liquid water somewhere in their interiors. A global ocean, entirely enclosed, entirely dark, heated from below, insulated from above. It is a strange and quiet thought. Out in the dark between the stars, moving in silence through the galaxy, there are worlds that carry within themselves an ocean that has never been touched by sunlight, that exists in conditions of total and permanent darkness, that is heated not by a star, but by the slow decay of elements older than the solar system itself. The warm heart within. It does not shine. It does not illuminate the frozen surface above it. It does not change the appearance of the planet from the outside, which remains a dark and featureless sphere moving silently through the interstellar medium. But it is there, persistent, quiet, warm in a universe that is almost everywhere cold. And in that warmth, as we will soon consider, something else might be possible, something that changes everything about how we think about these lonely worlds. Let us descend now. Let us leave the frozen surface behind, leave the brilliant starlit sky and the sharp ridges of ancient ice, and go downward, through the frozen crust, through the layers of compressed rock, through the darkness that is not the darkness of space but the darkness of depth, the darkness of rock, the darkness of a world that has sealed its secrets beneath kilometers of cold. We are going to visit the ocean. It begins, as you descend from the surface, with a gradual transition. The rock does not suddenly change character. It remains frozen, rigid, ancient, but the temperature rises a degree or two per kilometer at first, then more steeply as the radioactive heating in the deeper layers accumulates. After 10 kilometers, the temperature has risen, but it is still far below freezing. After 20 kilometers, it has risen further, but the frozen rock gives no sign of change. After 30 or 40 kilometers, the temperature in certain regions of the planet reaches a critical threshold, and the ice that exists in the pores and fractures of the rock begins, very slowly, to change state. The first liquid water appears not as a lake or a pool, but as a film. A microscopic film coating the surfaces of mineral grains within the rock, filling tiny cracks, occupying the spaces between crystals of silicate and oxide minerals. Brine, actually, because the minerals have been leaching ions into the water for billions of years, loading it with dissolved salts that depress its freezing point slightly below zero, allowing it to remain liquid at temperatures where pure water would have long since frozen. This briny film percolates slowly through the rock, driven by pressure gradients and temperature gradients, moving at rates that would be imperceptible on any human timescale, but moving nonetheless. And as you descend further, the water becomes more abundant. The fractured zone deepens, and the cracks and pores in the rock fill with liquid rather than ice. The water at these depths is under enormous pressure, the weight of 30 or 40 kilometers of rock pressing down from above, and that pressure changes its properties. High-pressure water has a higher boiling point, which means it can exist as a liquid at temperatures that would turn surface water to steam. The water in the deep fractured zone is hot by surface standards, perhaps 60 or 80 degrees, and it is under enough pressure to remain liquid at those temperatures, and it circulates, driven by the temperature gradient, rising where it is warm and sinking where it is cool. Below the fractured zone, the rock becomes more coherent, less porous. And somewhere in that transition, over a depth range that varies across the planet, the water that has been filling the porous spaces and fractures gives way to something more continuous. A layer where the rock has been dissolved and leached over billions of years to the point where the solid material is honeycombed with connected cavities, a zone of underground space that is not quite rock and not quite open water, but something in between, like the saturated rock of an aquifer, but deeper and under far greater pressure. And below that, in some regions of the planet, there is open water. An ocean. Not metaphorically, not in some limited or qualified sense. A genuine body of liquid water, perhaps tens of kilometers deep in places, occupying the lower regions of the planet's interior where the temperature is high enough to keep water liquid and the rock above is dense enough to confine it. An ocean that has never seen sunlight. An ocean that has been in this configuration since roughly the time the planet's surface froze, which means for hundreds of millions, perhaps billions, of years. An ocean that is warmed from below by the hot rock of the deep interior and insulated from above by the kilometers of frozen crust. This ocean is not still. The heat from below drives convection. Warm water rises from near the rocky bottom, where it has been in contact with the warm rock, and perhaps with hydrothermal vents, places where the hot rock has cracked and the warmest water from the deepest regions percolates upward through fissures, heated to temperatures that would be uncomfortable for us, but that represent a significant energy input to the ocean. That warm water rises, and cooler water from the upper regions of the ocean descends to replace it, and the whole ocean slowly turns in great convective cells, circulating over timescales of thousands or millions of years. The chemistry of this ocean is not the chemistry of any ocean on Earth. It has been evolving in isolation, sealed from the outside, for an almost incomprehensibly long time. The water has been in contact with the rock below and on all sides for billions of years, and that contact has shaped it profoundly. The minerals in the rock have been slowly dissolving, releasing iron and magnesium and calcium and silica and sulfur and dozens of other elements into the water. The water has become a complex chemical soup, its composition determined entirely by the particular mix of minerals in the planet's interior and the temperature and pressure conditions at each depth. It would be strange water by our standards. Heavily mineralized, rich in dissolved gases, where those gases can be generated by chemical reactions between the water and the rock, reactions like serpentinization, where water reacts with iron-bearing minerals and releases hydrogen. Rich in sulfur compounds, perhaps where the deep rock contains sulfide minerals that dissolve slowly into the water, slightly acidic in some regions, slightly alkaline in others, the pH varying with depth and location in the ocean in ways that reflect the local geology. And it would be dark. Absolutely and completely dark. There is no light source in this ocean. The rock above transmits no light because rock is opaque and the frozen crust above is kilometers thick. There is no bioluminescence, no chemiluminescence, no phosphorescence. The darkness is as total as darkness can be. Even the concept of visual experience becomes meaningless here. An eye in this ocean would perceive exactly the same thing regardless of whether it was open or closed. Nothing, not dim shapes, not faint shadows, nothing at all. And yet this ocean is not nothing. It is a highly organized chemical environment, maintained at temperatures and pressures that allow chemistry to proceed, driven by energy from the warm rock below. It contains the building blocks of complex molecules. It contains interfaces between rock and water where mineral surfaces can catalyze chemical reactions. It contains gradients of temperature and chemistry that drive things to happen. It has all of the physical and chemical characteristics of the kind of environment that, on Earth, we associate with the possibility of life. On Earth, the deep-sea hydrothermal vents, the places where hot mineral-rich water emerges from cracks in the ocean floor, are among the most productive ecosystems on the planet. Life there does not depend on sunlight at all. It depends on the chemical energy available in the vent fluid, on the reactions between the hot mineral-rich water and the surrounding seawater, on the gradients of chemistry and temperature that drive metabolism. Entire communities of organisms, from bacteria to tube worms to shrimp and fish, exist in total darkness at pressures that would crush a human, sustained entirely by chemical energy with no connection to the surface or the sun. If such life is possible at Earth's hydrothermal vents, then the question of whether something similar might be possible in the hidden ocean of a rogue planet is not obviously absurd. It is, in fact, a question that some scientists take seriously. Not because we have any evidence of life in these distant and inaccessible places, but because the conditions seem, in the most important respects, to be similar to the conditions that produced life on Earth. We will return to that question later, because it deserves its own consideration. For now, let us simply stay with the image of the ocean itself. This vast, dark, warm, mineral-rich body of water moving in its slow convective circulation, sealed beneath kilometers of ice, isolated from the universe outside, unaware in any sense of the frozen surface above or the stars beyond that. An ocean that has been doing this for a very long time. An ocean that has never been visited, that will likely never be visited, that carries its chemistry and its heat and its slow motion through the galaxy alongside the frozen world that contains it. There is something profoundly quiet about this image. The ocean inside a rogue planet is perhaps the most isolated body of water in the universe, more isolated than any deep-sea trench, more isolated than the hidden ocean beneath the ice of Europa. It is sealed not just by ice above it, but by the entire void of interstellar space outside the world that contains it. No connection to any other system. No tidal interaction with a nearby moon of significance. No seasonal variation driven by the angle of sunlight. Just water, in the dark, kept liquid by the warmth of ancient radioactive elements, slowly circulating, slowly dissolving rock, slowly building complexity, one reaction at a time, one mineral dissolution at a time, one organic molecule at a time. Not hurrying. The rogue planet is not hurrying, and neither is its ocean. They have all the time in the universe. We have been thinking about the rogue planet as a solitary world, and in the deepest sense it is. But the story of its solitude is not simple, because before it was truly alone, before it was in the interstellar dark with only the distant galaxy for company, it had relationships. It had connections. It had, in the physical sense, bodies that pulled at it and that it pulled back. And the evidence of those relationships, the ghost of those gravitational bonds, is still present in the planet, still detectable in its interior, still shaping the slow geological story of a world that looks, from the outside, as though it has been beyond the reach of any influence for billions of years. The most immediate of those former relationships was with the small moon that survived the ejection. In the early period of the rogue planet's journey, that moon was still there. A small rocky body, perhaps a few hundred kilometers across, orbiting the planet at a distance of perhaps a few thousand kilometers. Close enough for its gravity to be felt. Close enough for the planet's gravity to raise a tidal bulge on the moon and for the moon's gravity to raise a tidal bulge on the planet. Tidal forces, the differential pull of gravity across the diameter of a body, the force that, on Earth, drives the tides of our oceans, pulling the sea on the side nearest the moon slightly toward it and pulling the sea on the far side slightly away, creating the familiar rhythmic rise and fall of the tide. On the rogue planet, in the early period of its journey, those tidal forces did something more than raise ocean tides. Because the moon was close, and because the planet was cooling but still had a partially molten or at least mechanically weak deep interior, the tides were not merely a surface phenomenon. The solid body of the planet was being flexed very slightly with every orbital period of the moon. The rock of the deep interior was being squeezed and stretched in a cyclical rhythm, and that squeezing and stretching generated heat. Tidal heating, the same process that keeps the interior of Jupiter's moon Io volcanically active today, the same process that keeps the ice shell of Europa warm enough to maintain its hidden ocean, the same process that is responsible for much of the geological activity of the moons of the outer solar system. In the early period of the rogue planet's journey, tidal heating added an extra energy source to the interior. Not a large one. The moon was small and the orbit was not highly elliptical, which means the tidal flexing was not as intense as it would have been for a moon on a more eccentric orbit. But it was something, an additional warmth, an additional contribution to the energy budget of a world that was already losing heat rapidly to the surrounding cold of space. That moon did not stay forever. The dynamics of a moon orbiting a planet that is itself orbiting nothing are more complex than the dynamics of a moon in a solar system. In a solar system, the sun provides a stable reference frame for the planet's orbit, and the moon's orbit is perturbed only slowly over geological timescales. But for a rogue planet moving through the interstellar medium, occasionally passing through regions of slightly varying gravitational potential, occasionally coming close to distant stars over the course of millions of years of travel, the moon's orbit is less stable. Small perturbations accumulate. The orbit slowly changes. It becomes more eccentric, or it shifts its orientation, or the tidal interactions with the planet cause the moon to slowly spiral inward or outward, depending on the relationship between the moon's orbital period and the planet's rotation period. Over hundreds of millions of years, the rogue planet eventually lost its moon. Perhaps the moon's orbit decayed, spiraling inward until it crossed the Roche limit, the distance at which tidal forces from the planet exceed the gravitational self-attraction of the moon itself, and was torn apart. The resulting debris would have formed a ring around the planet for a time, a ring like the rings of Saturn, but composed of the shattered remnant of an entire moon. That ring would itself have been temporary. The particles in it would have gradually been swept up by the planet or pushed to unstable orbits by the planet's irregular gravity and the perturbations of passing objects. Over time, the ring would have thinned and disappeared, leaving perhaps a final enhancement of the cratering rate on the planet's surface as the last ring particles fell inward. Or perhaps the moon's orbit was perturbed outward instead, by a passing encounter with a distant star, and it eventually reached escape velocity and departed into the interstellar medium on its own trajectory. A moon without a planet, another dark object moving silently through the galaxy, but smaller and simpler than its former parent. Either way, the moon is gone, and its departure changed something. When the tidal heating stopped, the interior of the rogue planet lost one of its sources of warmth. Not the dominant source, which was and remains the radioactive decay in the rock, but a contribution that had been there, steady and reliable, for the first 100 million or several 100 million years of the journey. When the moon departed, that contribution vanished. The interior of the planet cooled a little faster as a result. The underground ocean, if it existed at that time, may have shrunk slightly in extent. The lower boundary of liquid water in the deep rock may have moved a little deeper, retreating from the surface as the warmth that had sustained it at shallower depths declined. The ghost of the moon is still present in the interior of the planet. Not in any direct material sense. The moon is gone, and its matter is elsewhere. But in the thermal history of the planet, in the pattern of heat that is encoded in the rock and in the structure of the underground ocean, the moon's tidal heating left a record. A layer of the rock that was warmed by tidal flexing during the period of the moon's orbit retains a slightly different structure, a slightly different crystal morphology than rock that was heated only by radioactive decay. These differences are subtle. They are the kind of thing that would require detailed analysis to detect, but they are there. The tidal remnant is the physical memory of a relationship. And there are older tidal memories too. Before the ejection, when this planet was still part of its solar system, it had gravitational relationships with the giant planets that eventually expelled it. During the period of close encounters that led to the ejection, the tidal forces on this planet were enormous. The close pass of a gas giant, a world tens or hundreds of times more massive than this planet, at a distance of only a few planetary diameters, would have subjected the planet to tidal forces that dwarfed anything a small moon could generate. The rock of the planet, during those close passes, was squeezed and stretched to the point of generating significant heat. The deep interior, already warm from formation heat and radioactive decay, received an additional pulse of tidal warmth. The crust, already under geological stress, may have fractured in new patterns during the encounter, opening new fault systems, triggering new volcanic activity. The entire body of the planet was reshaped at a deep level, by the tidal interaction with the giants that expelled it. Those deformations are encoded in the rock. The fault lines opened during the final close encounter are still present, deep in the frozen crust. The volcanic activity triggered by tidal heating during the encounter period left features on the surface that are still visible. The thermal pulse that reached the deep interior during the close passes created a brief period of enhanced geological activity that left its mark in the layered record of the deep rock. All of these are tidal remnants, the fingerprints of relationships that ended billions of years ago, preserved in the frozen and silent interior of a world that has been alone ever since. There is something poignant in the idea of tidal remnants. In the warm and mobile interior of a geologically active planet, such records would be erased fairly quickly. New geological activity would overwrite old features. New rock would cover old structures. The planet would forget its history, in a geological sense, within hundreds of millions of years. But the rogue planet does not forget. Its frozen surface and its slowly cooling interior preserve everything. The tidal forces that shaped it during its formation and ejection and early lonely journey are still present as structural features, as thermal gradients, as crystal patterns in the deep rock. They are the memories of a world that once had company, a world that was once part of something larger, something connected, something that pulled at it and was pulled by it in return. Now that company is gone, the pulling has stopped. The rogue planet moves through a gravitational field that is smooth and vast and diffuse, the general field of the Milky Way rather than the intimate tug of a nearby massive object. No tides of any significance disturb its interior anymore. The ocean, deep within, circulates on its own thermal energy, undisturbed by any external rhythm. The world is, at last, truly alone. And in that aloneness, something very quiet is happening. Something that has been happening for a very long time. Something that requires no outside influence, no tidal partner, no sun, no wind, no external event of any kind. Just the slow chemistry of water and rock, heated by the decay of atoms that have been counting down since the solar system's formation, deep in the dark, in an ocean that no light has ever touched. The rogue planet does not travel through a true vacuum. This is one of the facts about interstellar space that is easy to overlook, because we tend to think of the space between the stars as empty, as nothing, as the absence of anything. But the interstellar medium, the material that fills the galaxy between its stars, is not nothing. It is something thin, extraordinarily thin by any standard we could apply in a laboratory, but present, always present. A gas of atoms and molecules and tiny dust grains and energetic particles that threads through the entire galaxy, filling the spaces between the stars with a diffuse but real physical medium. The rogue planet moves through this medium, and the medium leaves its mark. The interstellar medium is not uniform. It has regions and structures, denser clouds and thinner voids, warm phases and cold phases, regions where the gas is ionized by the radiation from nearby hot stars and regions where it is neutral and cold. The average density of the interstellar medium is extraordinarily low, perhaps 1 atom per cubic centimeter in the typical regions between the stars. That is a vacuum so complete that any laboratory on Earth would be proud to achieve it. But the rogue planet is large, and it has been moving for billions of years, and even at 1 atom per cubic centimeter, the total amount of material it has swept through is significant. As the planet moves through the interstellar gas, atoms and molecules from that gas occasionally strike its frozen surface. The rate is slow, very slow, but over hundreds of millions of years, the accumulation adds up. Hydrogen atoms, the most abundant constituent of the interstellar medium, settle onto the surface of the ice and bond to the ice molecules there. Helium atoms, noble and unreactive, simply bounce off or sit loosely on the surface without bonding. Heavier atoms, carbon and oxygen and nitrogen, though rare in the interstellar medium, can react with the surface ice and become incorporated into it, adding their chemistry to the already complex mixture of frozen gases. In the denser regions of the interstellar medium, the encounters are more frequent. The galaxy is not a uniform environment. There are regions where the interstellar gas is concentrated into clouds, where the density might be hundreds or thousands of times greater than the average. These molecular clouds are the birthplaces of stars, regions where the gas is dense enough and cold enough for gravity to begin pulling it together, for chemistry to produce complex molecules, for the slow process of star formation to begin. When a rogue planet passes through one of these clouds, the rate of encounters with interstellar material increases dramatically. A molecular cloud is not a solid object. It does not have a sharp boundary. It is more like a region of higher density gas, a thickening of the interstellar medium, a place where the atoms are closer together. But from the perspective of a rogue planet moving through it, the change is real and measurable. More impacts, more chemistry, more material being added to the surface, and something else, something more dramatic. Molecular clouds are cold, far colder than the average interstellar medium, which is already extraordinarily cold. In the densest parts of a molecular cloud, the temperature can drop to 10 or 15 degrees above absolute zero. At these temperatures, complex chemistry becomes possible. Molecules form on the surfaces of dust grains within the cloud, reactions that would be too slow to occur in warmer regions of the galaxy. Carbon chains, alcohols, amino acids in their simpler forms. The interstellar medium is a chemical laboratory of extraordinary subtlety, producing organic molecules in the cold dark before any star has formed. When the rogue planet passes through such a cloud, it is bathed in this chemical richness. The molecules of the cloud, both in the gas phase and in the form of ice coatings on dust grains, interact with the planet's frozen surface. Some of those molecules are incorporated into the surface ice, adding to its chemical complexity, layering new organic material over the older layers of frozen atmosphere and earlier interstellar deposits. The planet emerges from the cloud carrying a new coat, a thin but chemically significant layer of material from the molecular cloud, organic molecules, exotic ices, the fingerprints of chemistry that happened in the cold dark between the stars. This material joins the archive that the surface is already building, the cumulative record of everywhere the planet has been, written in the chemistry of its ice. But the encounters with the interstellar medium are not only chemical. They are also energetic. The interstellar medium contains cosmic rays, which are not rays in the traditional sense, but highly energetic particles, mostly protons, traveling through the galaxy at nearly the speed of light. These particles are produced by supernova explosions and other energetic events, and they thread through the entire galaxy, passing through the interstellar medium and through anything in their path, including the rogue planet's frozen surface. Cosmic rays penetrate. They do not simply bounce off the surface of the ice. They travel deep into it, sometimes to depths of meters, before their energy is absorbed by interactions with the ice molecules they encounter along the way. And as they travel, They break chemical bonds. They create free radicals and reactive intermediates. They drive chemistry that would not otherwise be possible in the cold and dark. They convert simple molecules into more complex ones. They alter the structure of the ice at a molecular level. The cosmic ray bombardment has been ongoing since the moment the planet entered interstellar space. Billions of years of energetic particle impacts, each one tiny, each one affecting only a small volume of ice, but collectively transforming the upper layers of the surface ice into something chemically far more complex than the simple frozen gases that initially fell there. The surface ice of a rogue planet that has been in interstellar space for billions of years is, at a molecular level, an extraordinarily rich chemical environment, a place where cosmic ray-driven chemistry has had enormous amounts of time to operate. There is another interaction with the interstellar medium that is worth thinking about. The rogue planet, as it moves through the galaxy, is also moving through the galactic magnetic field. The Milky Way, like other spiral galaxies, has a large-scale magnetic field, tangled and irregular but present throughout the disk. This field is embedded in the ionized component of the interstellar medium, and as the rogue planet moves through it, there are interactions between the field and any charged particles in the vicinity of the planet. The planet itself is not a charged object, but it is not entirely neutral either. The cosmic ray bombardment of its surface creates some charged particles. The interaction between the surface ice and the interstellar gas creates some local ionization. These interactions are weak and their effects are subtle, but over billions of years, the cumulative influence of the galactic magnetic field on the environment immediately around the rogue planet is not entirely negligible. Perhaps the most striking encounter between the rogue planet and the interstellar medium is the encounter with a shock wave. Supernova explosions, the deaths of massive stars, send enormous waves of energy and material through the interstellar medium. These shock waves travel outward from the explosion site at thousands of kilometers per second, compressing and heating the gas they pass through, sweeping up material into dense shells, and eventually slowing and merging with the surrounding medium. They can travel for hundreds of light years before losing their character as distinct shock fronts. A rogue planet in the path of such a shock wave would experience something remarkable. The compressed gas of the shock front, arriving at velocities of hundreds or thousands of kilometers per second, would impact the planet's surface. The ram pressure of the encounter would be far greater than the gentle pressure of the ordinary interstellar medium. The outermost layers of the surface ice would be ablated, sputtered away by the intense bombardment of high-velocity gas particles. The chemistry of the surface would be disrupted and reset. A new surface layer would begin forming from the material deposited by the shock wave itself. The shock wave's passage would also heat the surface very slightly, very briefly, before the compressed gas moved on. Not enough to melt the ice below the thin, ablated layer. Not enough to fundamentally change the character of the surface, but enough to be recorded as a chemical and structural discontinuity in the surface archive, a layer that is different from what came before and what came after. Another entry in the diary of the planet's journey, written this time in the disrupted ice of a supernova's dying breath. These encounters with the interstellar medium, chemical and energetic and magnetic and occasionally violent, are the rogue planet's only ongoing relationship with the universe around it. It has no sun, it has no moon, it has no solar wind to interact with, no planetary neighbors to exchange gravitational energy with. But it does have the interstellar medium. thin and diffuse and extraordinarily cold, but present, always present, touching the surface of the frozen world in the dark, molecule by molecule, particle by particle, building up its archive layer by layer. It is the most minimal of relationships, the most tenuous of connections, a world touching the universe one atom at a time, one cosmic ray at a time, one organic molecule deposited from a passing molecular cloud at a time. But in the vast loneliness of interstellar space, it is something, a reminder that even the most isolated object in the galaxy is not entirely without contact, that the universe, diffuse and dark as it is in the spaces between the stars, still reaches out, still touches, still leaves its mark on everything that passes through it. We have been describing the rogue planet in terms of its structure, its surface, its interior, its encounters with the interstellar medium. But we have not yet properly sat with the most fundamental aspect of its existence, the time, the sheer, incomprehensible, humbling duration of its journey. Because the rogue planet does not travel for years or centuries or even millions of years before arriving somewhere meaningful. It travels for billions of years. And in all of that time, in all of those billions of years of motion through the dark, almost nothing changes. Almost nothing happens. This is, for the human mind, one of the most difficult things to absorb about the rogue planet. We are accustomed to time as a medium of change. In human experience, things happen in time. Seasons change. Children grow. Civilizations rise and fall. Even on geological timescales, things change. Mountains are built and eroded. Oceans open and close. Life evolves from simple cells to extraordinary complexity. Time, in every context we normally use it, is the dimension along which things happen. But for the rogue planet, time is mostly the dimension along which nothing happens. Consider what the planet has been doing for the last billion years. It has been moving through the interstellar medium at a velocity of roughly 20 or 30 kilometers per second relative to nearby stars, the typical velocity of objects in the galaxy's disk. At that speed, in a billion years, it has traveled something like 30,000 light years, a significant fraction of the width of the Milky Way's disk. It has crossed from one part of the galaxy to another, passing through regions with different stellar densities, different interstellar medium conditions, different positions relative to the spiral arms. And in all of that journey, on the surface of the planet, almost nothing has changed. The ice that was frozen when the atmosphere fell is still frozen. The craters from the early period of the journey are still exactly as they were formed. The ridgelines pushed up by ancient geological activity are still sharp and unchanged. The chemical layers in the surface ice have accumulated slowly, one molecular deposit at a time, building up at a rate so slow that a billion years of accumulation might represent only a fraction of a millimeter of new material. Below the surface, in the deep interior, the radioactive heating continues, slowly declining as the radioactive elements are used up, but declining so slowly that on the billion-year timescale, the change is modest. The underground ocean, if it exists, continues its slow convective circulation. The chemistry of the water continues its slow evolution, one dissolved mineral at a time, one chemical reaction at a time. These processes are happening, but they are happening at rates that make geological processes on Earth seem rapid by comparison. To understand what a billion years of this means, it helps to try some comparisons, even though all comparisons ultimately fail. If the entire history of the rogue planet's journey were compressed into a single year, and the planet had been traveling for 4 billion years since its ejection, then the entire history of human civilization would occupy less than the last 2 seconds of that year. The dinosaurs would have appeared and disappeared in the last few minutes. The formation of Earth's oceans would have happened in early December. The origin of life on Earth would have occurred in late spring. Everything that we think of as history, everything that has ever happened in the recorded or unrecorded memory of our species, would be a vanishingly small fraction of the rogue planet's journey. And the rogue planet, during all of that equivalent year, would have been doing exactly what it is doing right now, moving, slowly, through the dark, unchanged on its surface, quietly warm in its interior, carrying its ocean in the deep rock, moving through the galaxy. The motion itself follows a particular kind of path. The rogue planet is not moving in a straight line. Nothing in the galaxy moves in a straight line. The galaxy is a gravitational environment of enormous complexity, with the combined mass of hundreds of billions of stars creating a potential well that curves space in all directions. An object moving freely through the galaxy, not bound to any particular star, follows what is called a galactic orbit. Not an orbit around a single point, but a complex path shaped by the overall distribution of mass in the galactic disk and halo. For an object in the disk of the Milky Way, this orbit typically has 2 components. A circular component, an average motion around the galactic center at a speed of roughly 220 kilometers per second for objects at our distance from the center, and an oscillatory component, a bobbing motion up and down through the plane of the disk, driven by the gravitational attraction of the disk material. The rogue planet moves around the galaxy in this complex path, taking roughly 200 million years to complete one circuit of the galactic center and oscillating above and below the galactic plane with a period of roughly 100 million years. In 4 billion years, it has completed perhaps 20 circuits of the galactic center. It has bobbed through the galactic plane perhaps 40 times, each time passing through the denser regions of gas and dust and stars near the plane, and each time rising into the relatively less dense regions above and below the plane. It has passed through the outskirts of several spiral arms, regions of slightly enhanced stellar and gas density that rotate around the galaxy at a different speed from the stars themselves. During all of these passages, the planet has encountered other stars. Not closely, not in any way that would dramatically alter its trajectory. But the galaxy is not so empty that a planet can travel for 4 billion years without occasionally passing within a few light years of another star. Statistically, a typical rogue planet in the disk of the Milky Way should make a moderately close approach, within a few light years, of another star every few hundred million years. Not close enough for a strong gravitational interaction. Not close enough to affect the planet's trajectory significantly. Those stellar encounters are the closest thing the rogue planet has to events, to moments that stand out against the vast background of unvarying silence of the journey. A star approaching, brightening over the course of tens of thousands of years as the geometry of the encounter develops, reaching a peak brightness that might be comparable to a full moon or even brighter, and then fading again over the following tens of thousands of years as the relative velocity of the 2 objects carries them apart. A brief illumination, a faint additional warmth on the frozen surface, and then darkness again, and then the motion continues. What does it mean for something to simply continue for this long? It is a question that resists a satisfying answer. Our sense of meaning is shaped by narrative, by change, by progression from one state to another. We understand things in terms of beginnings and middles and ends, in terms of events and consequences, in terms of processes that lead somewhere. But the rogue planet's journey does not lead somewhere in that sense. It is not building toward anything. It is not resolving anything. It is not completing a cycle in any meaningful way. It is simply continuing, moving, persisting, and yet it is not meaningless. The rogue planet is not doing nothing. It is maintaining its existence, which requires a great deal of ongoing physics to accomplish. Its gravity holds it together. Its internal heat sources prevent the deep interior from reaching absolute zero. Its geological structure, though frozen and static at the surface, is still slowly evolving in the deep rock. Its ocean is still circulating. Its chemistry is still proceeding. It is not a passive object. It is an active system, running on the energy of its own formation and the radioactive decay of its constituent elements, maintaining its internal organization against the entropy that would otherwise degrade it. It is, in the most literal sense, persisting. Against the cold, against the dark, against the billions of years of silent motion that might, if we were not careful in our thinking, seem to dissolve everything into meaninglessness. It persists. It carries its ocean. It carries its frozen surface and its internal heat and its chemical complexity and its tidal scars and its archive of interstellar encounters. It carries all of this through the galaxy, year by year, century by century, millennium by millennium, billion years by billion years. There is something in this persistence that feels important, something that is worth sitting with, not rushing past in the effort to reach the next interesting fact. The rogue planet has been doing this for longer than life has existed on Earth, for longer than the Earth itself has existed, for a time so vast that the entire story of our planet, from its formation to its eventual end billions of years from now, would fit inside the rogue planet's journey with room to spare. And in all of that time, it has simply continued, moving through the dark, carrying its warmth, keeping its ocean, asking nothing of the universe, receiving almost nothing from it, persisting. There is, in that persistence, a kind of dignity, a kind of quiet strength that has nothing to do with drama or achievement or arrival, a strength that consists simply in continuing, in maintaining what one is against all of the pressures that would change it, in carrying one's internal warmth through the cold, in keeping one's depths liquid when the surface is frozen, in moving through the dark without requiring the dark to be anything other than what it is. Billions of years of silent motion, not an emptiness, not a waste, simply the deepest expression of what it means to persist. In all of the vast journey of the rogue planet, there is one class of encounter that is qualitatively different from all the others. Different from the encounter with the interstellar gas, different from the distant stellar flyby, different from the passage through a molecular cloud. This is the encounter with another solar system. A system with a star at its center, with planets in orbit, with the warm and complex environment that represents everything the rogue planet lost when it was ejected from its own home. These encounters happen, not frequently, not dramatically, but they happen. A rogue planet moving through the disk of the Milky Way will, over the course of billions of years, occasionally pass through or near a solar system. The geometry is almost always distant. The rogue planet's trajectory, which is determined by its velocity and the large-scale gravitational field of the galaxy, might bring it through the outermost reaches of another system's cometary cloud, the vast diffuse halo of icy bodies that surrounds every solar system at distances of thousands of astronomical units. Or it might pass more closely through the region of the outer planets, the cold and dark realm beyond the equivalent of Neptune. Or very rarely, following an improbable trajectory, it might pass through the inner reaches of a solar system, through the zones where planets warm enough for liquid water orbit. Let us think about what each of these encounters is like. The passage through the outer cometary cloud of another solar system is the most common encounter and the quietest. At distances of thousands of astronomical units from the central star, the solar system is represented primarily by a vast population of small icy bodies, comets in their unactivated state, orbiting the star in extremely elongated paths that carry them slowly through the outer dark. These objects are loosely gravitationally bound to their star. The binding energy of a comet in the outer cloud is very small compared to the binding energy of a planet close to its star. It does not take much to perturb one of these distant comets out of its orbit. As the rogue planet passes through this outer region, its gravity perturbs the comets it passes near. Some comets are nudged into new orbits that will eventually carry them inward toward the central star, where they will become the bright-tailed objects we see in our own sky. Others are nudged in the opposite direction, pushed into orbits that are unbound from the star, and they too become rogue objects, smaller than our planet but similarly free, moving through the interstellar medium on their own journeys. The rogue planet sweeps through this outer cloud like a slow and massive hand, rearranging the orbits of thousands of small bodies, triggering a long-delayed cometary shower toward the inner solar system that may arrive over the course of millions of years after the encounter itself. The star system experiences the rogue planet's passage as an unusual enhancement of cometary activity, a rain of icy visitors from the outer dark that represents the gravitational wake of an encounter that happened so long ago and so far away that no one in the inner system could observe it directly. A closer passage through the region of the outer planets is more dramatic. If the rogue planet passes within the orbit of the outermost planets, the gravitational interaction becomes significant, not just for small comets and scattered debris, but for the planets themselves. The rogue planet, passing at high velocity on a hyperbolic trajectory through the outer solar system, perturbs the orbits of the outer planets. The perturbations are not enormous, because the rogue planet is moving quickly and the interaction time is limited. But they are real. They shift the orbital parameters of the outer planets slightly, changing the eccentricities and inclinations of their orbits. These perturbations can have long-term consequences. A slight shift in the orbit of an outer planet can, over millions of years, propagate inward through gravitational interactions between the planets, potentially affecting the orbits of inner planets, potentially triggering the same kind of gravitational resonance cascades that ejected our rogue planet from its own solar system. In a very real sense, a rogue planet passing through a solar system may be planting the seeds of future ejections. Future rogue planets, set in motion by the gravitational echo of a passing wanderer. And from the perspective of the rogue planet itself, the close passage through a solar system is the nearest thing it will ever experience to a return home. For a period of years or decades, depending on the geometry of the encounter, the rogue planet moves through a space that is not entirely dark. There is a star, not the rogue planet's star, not the star it once orbited, but a star, a source of light and warmth, growing brighter as the planet's hyperbolic trajectory curves around the inner system, and then dimming again as the trajectory carries it back outward into the interstellar dark. The warmth from the star, brief and not intense at the distances involved, does something to the rogue planet's frozen surface. The outermost layers of ice, chilled to near absolute zero for billions of years, suddenly find themselves exposed to a faint but real thermal flux. The temperature of the surface ice rises slightly, perhaps only by a fraction of a degree, perhaps in a very close encounter by more. Where the temperature rises enough, the surface ice sublimates slightly, releasing trace amounts of gas into the near vacuum above the surface. For a brief time, the rogue planet has a tenuous exosphere, a ghost of an atmosphere, as the most volatile surface ices respond to the unexpected warmth. This sublimated gas glows faintly in the sunlight of the passing star. The rogue planet, dark and invisible in ordinary interstellar space, briefly becomes detectable. It develops a coma, a faint haze of gas surrounding the solid body, like a comet's coma, driven by the same sublimation process. If the encounter is close enough and the star bright enough, the rogue planet might even develop a tail of sorts, a stream of gas pushed away from the star by radiation pressure, a temporary feature that announces its presence to any observer in the star system it is passing through. The inner planets of the solar system, if any civilization exists on them, might observe this visitor as an unusual object in their sky. Not a normal comet, because it is too massive and too large. Not a planet of their system, because its trajectory does not close into an orbit. Something in between, something that appears in their outer solar system, brightens slightly, and then moves on toward a different part of the sky. A temporary mystery, a visitor that was passing through long before the civilization formed, and will still be passing through if the civilization never forms at all. And then the encounter ends. The star recedes. The warmth fades. The ghost atmosphere refreezes onto the surface, adding a new chemical layer to the archive, a layer with a slightly different composition because it includes the material sublimated and redeposited during the encounter. The rogue planet returns to the dark. Its surface is once again at near absolute zero. The stars are once again just stars, points of light in a dark sky. And the motion continues. There is something moving about this encounter between the rogue planet and the solar system it passes through. The rogue planet carries within it the memory of its own solar system, encoded in its geology and chemistry and thermal structure. And for a brief period, it passes near another solar system, another star, another collection of worlds. The two systems exchange nothing directly. The rogue planet does not communicate its history. The solar system does not offer the rogue planet a home. But gravitationally, they touch. The gravity of the rogue planet reaches into the solar system and disturbs its outer objects. The gravity of the star perturbs the rogue planet's trajectory very slightly, bending its path by a fraction of a degree before releasing it back into the interstellar dark. They are connected, briefly, by the most fundamental force in the universe. And then they are separated again, moving apart at velocities that make reunion impossible. Two worlds, two histories, one moment of connection, and then the long silence again. The rogue planet continues outward, carrying the chemical record of its brief encounter with a star in the sublimated and redeposited layer on its surface, carrying the memory, in the slight curve of its trajectory, of a gravitational interaction that happened for a decade and will be forgotten by everyone. Carrying all of this back into the dark, back into the billions of years of motion, back into the silence and the cold and the galaxy wheeling slowly overhead. It is a reminder that even in the most isolated journey, even in the deepest solitude, moments of contact occur. Quiet, brief, gravitational contacts. Touches of gravity between objects that will never meet again. And something is always left behind by those contacts. Something always changed, however slightly, by the moment of connection. That seems like something worth knowing. We have been following the rogue planet through its long journey, describing its surface and its interior and its encounters and its billions of years of motion. But there is a question that underlies all of this description that deserves its own careful attention. How do we know any of this? How do we find objects that do not shine, that do not orbit anything, that leave almost no trace of their passage through the galaxy? How do we detect the undetectable? The answer involves some of the most ingenious methods in all of astronomy. Methods that turn the fundamental properties of physics into instruments of discovery, that use the behavior of light and gravity to reveal objects that would otherwise be permanently hidden. It is a story of indirect evidence and patient observation, of waiting for the universe to reveal its secrets one brief alignment at a time. The primary method for detecting rogue planets is called gravitational microlensing. It is a technique that would have seemed like fantasy to astronomers of a century ago, but that rests on a consequence of general relativity that Einstein himself predicted. Gravity bends light. Any massive object, any object with gravity, curves the fabric of space-time around it, and light follows the curve. A beam of light passing near a massive object is deflected, bent slightly toward the object, in the same way that a beam of light is bent when it passes through a glass lens. The analogy with a lens is more than decorative. A massive object in space acts, optically, like a lens. It can focus light from a background source, concentrating it, brightening it, creating magnified or distorted images of whatever lies behind it. This is gravitational lensing, and it has been observed in dramatic form in images of distant galaxy clusters, where the enormous mass of a cluster bends and distorts the images of galaxies billions of light years behind it into arcs and rings of extraordinary beauty. Microlensing is gravitational lensing on a much smaller scale. Instead of a galaxy cluster acting as the lens, it is a single star or a single planet. And instead of producing dramatic arcs and rings visible in images, it produces a subtle brightening of a background star that lasts for hours or days or weeks, depending on the mass of the lensing object and the geometry of the alignment. Here's how it works. A rogue planet moves through the galaxy, following its orbit, moving at its typical velocity of tens of kilometers per second relative to the stars around it. Occasionally, by pure geometric chance, its trajectory carries it precisely between Earth and a distant background star. The rogue planet's gravity acts as a tiny lens. It focuses some of the background star's light toward us. The star appears to brighten slightly for a period of hours to days, and then returns to its normal brightness as the rogue planet continues on its way. The entire event happens once, briefly, and never repeats. The rogue planet has moved on. The alignment that produced the lensing event is a configuration that will never occur again. All that remains is the data, the record of a brief brightening in the light curve of a distant star, recorded by an observatory that happened to be watching at the right moment. From that brief brightening, astronomers can extract a remarkable amount of information. The duration of the brightening tells them about the mass of the lensing object and the relative velocity between the lens and the background star. The shape of the light curve, the way the brightness rises and falls, carries information about the geometry of the encounter. And crucially, the absence of any associated star, the fact that the brightening is not accompanied by any visible stellar object moving across the field of view, tells them that the lensing object is either a very faint star or a free-floating planet, a rogue. The challenge of this technique is the rarity of the events. For any given background star, the probability of a microlensing event occurring in any particular year is extraordinarily small. The fraction of the sky that a rogue planet occupies at any given moment is negligible. To make the technique work, you have to monitor enormous numbers of stars simultaneously, waiting for the rare alignment that produces a detectable brightening. This is why microlensing surveys point toward the densest regions of the galaxy, the bulge at the center of the Milky Way, where the density of both background stars and foreground objects is highest. Telescopes dedicated to microlensing surveys image millions of stars every night, recording the brightness of each star in every frame. Looking for the characteristic pattern of a microlensing event, a smooth and symmetric rise and fall in brightness that is distinct from the variable stars and other transients that also change brightness in the same data. The surveys have been running for decades, and they have detected thousands of microlensing events. Most of them are caused by stars. Some are caused by stellar remnants, white dwarfs, neutron stars, even black holes. And some, a significant fraction, are caused by objects with masses comparable to planets. Free-floating objects, not associated with any star, with masses ranging from a few times the mass of Jupiter down to something comparable to the mass of Earth. Rogue planets, or at least planetary mass objects in the interstellar medium. The statistics of these detections are extraordinary. Early analyses of the microlensing data suggested that rogue planets might be more common than stars in the Milky Way. More recent and more careful analyses suggest the number might be somewhat lower, but still remarkable, perhaps one to several Jupiter-mass rogue planets for every star in the galaxy. For Earth-mass rogue planets, the number might be higher still, because smaller objects are harder to detect and the detected sample likely underrepresents them. Microlensing is not the only method for finding rogue planets. For the more massive ones, particularly those with masses of several times Jupiter or more, direct imaging in infrared light becomes possible. Young rogue planets are warm, a planet that formed recently, within the last few 100 million years, retains significant heat from its formation. That heat causes it to glow in the infrared, not brightly, not with anything like the intensity of a star, but detectable with sensitive enough instruments against the dark background of the interstellar medium. Several objects discovered through infrared surveys and initially classified as very low-mass brown dwarfs have been reconsidered as rogue planets. The distinction between a very low-mass brown dwarf, a failed star that formed in the interstellar medium, and a rogue planet, a planet that formed in a solar system and was later ejected, is not easy to make from observations alone. Both objects would look similar to our instruments. The difference lies in their formation history, which leaves chemical signatures in their atmospheres that are in principle distinguishable, but in practice difficult to measure for distant objects. The Roman Space Telescope, designed partly for microlensing surveys, promises to revolutionize our knowledge of rogue planet populations. By monitoring an enormous number of stars with high cadence and high sensitivity, it will detect microlensing events caused by objects as small as the mass of Mars. The resulting census of free-floating planetary mass objects in the galaxy will be our most complete inventory yet of these dark wanderers. And there is another method, still in its early stages, that might eventually allow us to find rogue planets that are carrying liquid water. The theory predicts that planets with active geology or liquid water oceans might emit certain radio frequencies, the result of interactions between their magnetic fields and their surrounding environment. These emissions would be extraordinarily faint, and detecting them across interstellar distances would require instruments far beyond anything we currently have. But the principle is sound, and the universe has a long history of becoming observable once we build the right instrument. For now, what we know about rogue planets comes primarily from the microlensing statistics and from a handful of directly imaged candidates. We know they are common. We know they span a range of masses. We know they exist in large numbers throughout the disk of the Milky Way. We know, from theoretical modeling, that the physics of their interiors supports the existence of liquid water in many cases. We know that their surfaces record their chemical history in the accumulated ice. What we do not know yet is everything interesting. We do not know the composition of any individual rogue planet's surface or interior. We do not know whether any of them carry life. We do not know the detailed chemistry of their hidden oceans. We do not know how they are distributed across the galaxy, whether they are more common in some regions than others. We are, in relation to rogue planets, exactly where astronomers were in relation to exoplanets 30 years ago. We know they exist. We have a rough sense of how common they are. We have theoretical models that make predictions about their properties, and we are building the instruments that will eventually tell us much more. The dark wanderers are revealing themselves to us, slowly, one brief brightening of a distant star at a time. One ephemeral alignment between a traveling world and a background light, lasting for hours and never repeating. Each event a momentary signal from a world that has been moving in silence for billions of years. Each event a brief moment of contact between the hidden universe and our instruments. The rogue planets are telling us they are there. We are learning, slowly, to listen. We have been thinking about individual rogue planets, following one particular world through its long journey, imagining its surface and its interior and its encounters. But there is a question about the population as a whole that changes the feeling of the entire subject. Not how is a rogue planet, but how many are there? Not what is the experience of one dark wanderer, but what does it mean that the galaxy may be filled with them? The numbers, when you sit with them, are genuinely staggering. The Milky Way contains somewhere between 200 and 400 billion stars. That number alone is difficult to hold in the mind. If you tried to count to 200 billion, counting one number per second without pause, it would take more than 6,000 years. Every star in the galaxy is a sun, a nuclear furnace comparable to our own or larger or smaller, each one potentially with its own family of planets. Now consider the estimate that there may be 1 to several Jupiter mass rogue planets for every star in the galaxy. If that estimate is correct, the number of rogue planets in the Milky Way alone is comparable to the number of stars. 200 billion, 400 billion, perhaps more. A galaxy of dark worlds, invisible against the interstellar medium, moving silently through the same space as the stars, outnumbering them or matching them in quantity, while emitting almost none of the light they do. And for smaller rogue planets, the Earth mass and sub-Earth mass objects, the numbers may be higher still. Planetary formation theory suggests that smaller planets are more common than larger ones. The process that makes giant planets is less efficient than the process that makes rocky worlds. For every gas giant in a solar system, there are likely several rocky planets. And for every gas giant ejected from a solar system, there are likely several rocky planets ejected as well, though the statistics of ejection depend on mass and orbital dynamics in ways that are still being worked out. If the ratio holds even approximately, the number of Earth mass rogue planets in the galaxy could be several times the number of stars. Several times 200 to 400 billion. The number loses meaning at these scales. It is too large for intuition. But there is a different way to approach it, a way that brings the number back into focus. Instead of asking how many there are in the entire galaxy, ask how many there are in the vicinity of our solar system. In the region of space within, say, 100 light-years of the Sun. Within 100 light-years of Earth, there are roughly several thousand stars. If there is one Jupiter mass rogue planet per star, there are several thousand Jupiter mass rogue planets within 100 light-years. If there are several Earth mass rogue planets per star, there might be tens of thousands of Earth mass rogue planets within the same volume. Moving silently through the same patch of galaxy that we inhabit, dark and invisible, none of them closer than a light year or two at any given moment, but present, sharing our galactic neighborhood. Some of them have already passed through our solar system. Over the 4.5 billion-year history of the solar system, the probability of a rogue planet passing through the outer cometary cloud, the region beyond Neptune, is reasonably high. The probability of a close encounter in the inner solar system is much lower, but not zero. We would not necessarily know about these past encounters. A rogue planet passing through the outer solar system would perturb some comets and continue on its way, leaving a gradual increase in cometary activity that might not be distinguishable from the natural variability of the cometary flux. The thought that our solar system has already been visited by these dark wanderers, perhaps multiple times, is a curious one. We have almost certainly been in the presence of rogue planets without knowing it. They pass through the outer reaches of our system, dark and silent, their gravity nudging a few distant comets into new orbits, and then they continued on their way, already billions of years into a journey that will continue for billions more. We were here. They were here. The encounter left almost no trace. The sheer number of rogue planets also has implications for the question of life in the universe. If there are hundreds of billions of rogue planets in the Milky Way, and if a significant fraction of them carry liquid water oceans in their deep interiors, and if liquid water oceans are one of the key requirements for life, then the number of potentially habitable environments in the galaxy has just been multiplied enormously. We tend to think about habitability in terms of the habitable zone around a star. The zone where liquid water can exist on the surface. The zone where the temperature is just right. The Goldilocks zone. And we count the number of Earth-like planets in those zones and estimate the probability of life based on that count. But rogue planets represent an entirely different category of potentially habitable environment, one that is independent of stars entirely, one that is driven by internal heat rather than stellar warmth, one that is sealed and isolated rather than open to the surface. If life can exist in environments like the deep ocean hydrothermal vent communities on Earth, if it can survive and thrive in total darkness powered by chemical energy rather than sunlight, then the potential number of life-bearing worlds in the galaxy is not merely the count of Earth-like planets in stellar habitable zones. It is the count of all planets with liquid water anywhere, including all the rogue planets moving silently through the dark with their hidden oceans. and that count could be far larger than anything we have previously estimated. This is not to say that rogue planets are likely to harbor life. The barriers are real and significant. Liquid water in a closed system, isolated from star-driven chemistry, lacking the rich energy gradients that stellar systems provide at their surfaces, is a different environment from the hydrothermal vents of Earth's ocean floor. Whether the chemistry of rogue planet oceans is rich enough to generate the complexity required for life is genuinely unknown. It is a question that cannot be answered from our current vantage point. But the point is that the question is open, that the number of potentially relevant environments is so large that even a small probability of life per environment translates into a potentially enormous total number. That the galaxy, which already seemed rich with possibility when we counted only the stars and their planets, becomes even richer in possibility when we include the dark worlds moving between the stars. There is also the question of what happens over very long timescales. Rogue planets persist. They do not run out of energy the way a star eventually exhausts its nuclear fuel. They will continue to carry their internal heat, declining slowly, for timescales that are comparable to or longer than the current age of the universe. As the stars of the galaxy age and die, as the era of stellar nucleosynthesis gradually winds down over the next trillion years, the rogue planets will outlast most of them. In the very far future, when the last stars have cooled and the galaxy is dark, rogue planets will still be moving through the darkness, still warm inside, still carrying their oceans, still maintaining whatever chemistry their interiors sustain. The population of rogue planets represents not just the current dark census of the galaxy, but its future. They are the most durable objects in the universe that are also complex enough to be interesting. More durable than stars, which run out of fuel. More complex than black holes, which have destroyed their internal structure. Planets, particularly large rocky planets with radioactive heating and deep water, persist. They endure. They will be here long after the stars that formed them are gone. We live in an early era of the galaxy's history. The stars are still burning. The stellar nurseries are still active. The interstellar medium is still being enriched by supernova. It is a time of great activity and great light. But the rogue planets that are moving through this lively era are the same rogue planets that will be moving through the quiet, dark era billions of years from now. They are not visitors. They are permanent residents of the galaxy, outlasting nearly everything else the cosmos creates. The number of rogue planets is not merely a census figure. It is a statement about the nature of the galaxy, about the endurance of planetary mass objects, about the possibility of environments persisting long enough for chemistry to become extraordinary. It is a reminder that the dark is not empty, that the cold is not absolute, that the silence of interstellar space is not a silence of nothing, but a silence of very many somethings, moving steadily through the dark, each one carrying within it the compressed and ancient warmth of its formation. Hundreds of billions of dark worlds, moving, persisting, carrying their oceans, waiting for nothing, going nowhere in particular, but going and going and going through all the dark years of the galaxy's long life. We have arrived at the question that has been waiting beneath the surface of everything we have described so far. The question that changes the emotional texture of the whole subject. The question that turns a rogue planet from a cold and solitary geological curiosity into something that makes us lean forward slightly, something that makes the darkness between the stars feel different. Could life exist on a rogue planet? It is a question that scientists take seriously. Not because we have any evidence of life on rogue planets. We do not. We have never directly sampled a rogue planet, never analyzed its chemistry, never looked into its hidden ocean. We cannot. But taking a question seriously in science does not require evidence. It requires that the question be physically plausible, that the conditions it asks about are not obviously incompatible with what we know about how life works. And the conditions on a rogue planet with a liquid water interior ocean are not obviously incompatible. To understand why, we need to think carefully about what life actually requires. The traditional view of what life needs is centered on the sun. We imagine life as a process that begins with sunlight striking a surface, driving photosynthesis, building the chemical complexity that eventually produces organisms. We imagine the warm surface of a planet, the liquid water of an ocean under an open sky, the atmosphere carrying gases produced by living things and cycling them back into the environment. We imagine life as a surface phenomenon, dependent on starlight, connected to the sky. But this view is wrong. Or rather, it is incomplete. It describes one way that life can work, the way that happens to be most familiar to us because it is the way that dominates Earth's surface. But it is not the only way. In the 1970s, oceanographers made a discovery that permanently changed how we think about the requirements for life. Deep in the Pacific Ocean, at depths of more than 2 kilometers, far below the reach of any sunlight, they found hydrothermal vents, cracks in the ocean floor where seawater, having percolated down through the rock, is heated by the magma below and erupts back into the ocean as hot mineral-rich fluid. The temperature of the vent fluid can reach hundreds of degrees. The chemistry is extreme. The pressure at those depths would crush an unprotected human, and there is no light at all. Around those vents, they found life. Not a few hardy bacteria clinging to the edge of survivability. Entire ecosystems, dense and complex, thriving in the complete absence of sunlight. Tube worms meters long, crabs and shrimp and fish, dense mats of bacteria covering every surface. All of it powered not by photosynthesis, not by sunlight, but by chemosynthesis, by the chemical energy available in the reactions between the hot mineral-rich vent fluid and the surrounding seawater, by the oxidation of hydrogen sulfide and hydrogen and methane, reactions that release energy without requiring any light at all. These vent communities are not marginal. They are not barely surviving. They are flourishing, producing biomass at rates comparable to productive surface ocean environments. They are diverse. They have food webs. They have predators and prey. They have parasites and symbionts. They are fully realized ecosystems, as complex in their way as a tropical forest, existing in conditions that our sun-centered view of life would have predicted should be sterile. The discovery of hydrothermal vent ecosystems fundamentally changed astrobiology, the study of life in the universe. It demonstrated that liquid water plus chemical energy gradients plus mineral surfaces is sufficient to sustain life, without any requirement for sunlight. It demonstrated that the envelope of habitable conditions is far wider than we had previously imagined. And it made the question of life in icy ocean worlds, whether those are the moons of Jupiter and Saturn or the hidden oceans of rogue planets, not merely speculative, but physically well-motivated. Now return to the rogue planet. Its deep interior ocean has liquid water. We have established that. It has chemical energy gradients, the temperature difference between the warm rock below and the cooler water above, the chemical disequilibrium between the minerals in the rock and the water dissolving them. It has mineral surfaces, rock in contact with water over an area that is, given the scale of a planet's interior, enormous. It has been maintaining these conditions for hundreds of millions or billions of years. In every respect that matters for the hydrothermal vent ecosystems on Earth, the rogue planet's interior ocean resembles the deep ocean floor around a hydrothermal vent system. Not perfectly. There are differences. The energy available per unit area in a rogue planet's ocean may be lower than at an active vent. The chemistry may be different in specific ways. The physical conditions, particularly the pressure, are different. But the basic requirements, liquid water, chemical gradients, mineral interfaces, long duration, are all present. The question, then, is not whether the physical requirements are met. They are. The question is whether the specific combination of conditions in a rogue planet's ocean is sufficient to cross the threshold from chemistry to biology. And that is a question we do not know how to answer because we do not fully understand how life arose on Earth. The origin of life, the transition from complex chemistry to self-replicating, metabolizing, evolving systems, is one of the most profound unsolved problems in all of science. We know it happened on Earth. We know it happened within the first billion years of Earth's existence, because the geological record contains evidence of life that old. We know it involved chemistry in water, involving carbon-based molecules and mineral surfaces and energy gradients. But we do not know the precise sequence of steps. We do not know how many different pathways might lead from chemistry to biology. We do not know how probable the transition is, whether it requires extraordinary coincidences or whether it is almost inevitable given the right conditions and sufficient time. If the origin of life requires extraordinary coincidences, then rogue planets are probably lifeless. The conditions may be broadly right, but the specific sequence of events needed to generate life may be so improbable that it occurs only rarely even in favorable environments. In that case, life in the galaxy is rare, and the chances of it arising independently in the isolated interior of a rogue planet are small. But if the origin of life is more or less inevitable given the right conditions and sufficient time, then rogue planets become fascinating. Because they have all the conditions and they certainly have the time. A rogue planet that has been carrying its liquid water ocean for 1 billion years has had more time than the Earth needed to develop the first cells. And it has had that time in conditions that are in some ways simpler and more stable than the early Earth, which was subjected to enormous meteorite bombardment, dramatic changes in atmospheric chemistry, and other perturbations that may have disrupted early life several times. The rogue planet's interior ocean is stable, unchanging, protected from the outside universe by kilometers of frozen rock. Whatever chemistry begins there is not going to be disrupted by a large impact, because impacts on the surface do not penetrate to the interior ocean. It is not going to be sterilized by intense ultraviolet radiation from a nearby star, because it is sealed in the dark. It is not going to be disrupted by dramatic changes in atmospheric composition, because there is no atmosphere. The conditions that existed when the ocean first formed are, to a very large approximation, the conditions that exist today. Life, if it began in the rogue planet's ocean, has had uninterrupted time and uninterrupted conditions in which to evolve. The word evolve is important here, because even if life began in the rogue planet's ocean, the kind of life it could become is constrained by its environment in ways that are profound. There is no sunlight, so there is no selective pressure toward developing photosynthesis or light-sensitive pigments or eyes. There is no surface, So there is no selective pressure toward locomotion in a gravitational field, toward structures that support a body against gravity, toward behaviors that involve moving from one place to another in any directed way. What selective pressures would there be? The chemistry of the ocean, the availability of different molecules in different regions, the chemical gradients around the hydrothermal vents, the temperature differences between deep and shallow regions would all create selective pressures. Organisms that could move toward or away from particular chemical concentrations would have an advantage. Organisms that could tolerate the high pressure and high temperature near the vents would be able to exploit the richest energy sources. Organisms that could use a wider range of chemical reactions to generate energy would be more robust than those dependent on a narrow chemical niche. It would be utterly alien by the standards of anything we know. Not alien in the science fiction sense of having a different shape or different biochemistry, though it might well have different biochemistry, but alien in the sense of having no frame of reference in common with surface life. No sense of light or dark, no sense of above or below in any meaningful way. No seasons, no day or night, no weather, no variability of any kind in the environment. Just the slow chemistry of the deep water, just the warmth of the rock, just the dark. What would it mean to be alive in those conditions? It is almost impossible to imagine, but that is partly because we are surface creatures, creatures of light and air and open sky. Our imagination is shaped by our environment. The creatures of the hydrothermal vents, if they had imagination, would find the surface of the earth as alien and unimaginable as we find the deep vent environment. Neither perspective is more valid than the other. They are both life. They are both real. And that is the most honest answer to the question of whether life could exist on a rogue planet. It could. The physics permits it. The chemistry does not preclude it. The time available is sufficient. Whether it does exist on any particular rogue planet, whether the specific conditions of a specific world's interior ocean cross the threshold from chemistry to biology, we cannot say. We do not have the tools to know. But the question is open. The door is not closed. And in a universe containing hundreds of billions of rogue planets, each carrying its hidden ocean in the dark, the possibility that some of them are not merely warm and wet inside but alive is not a fantasy. It is a scientifically serious possibility, one that changes the entire feeling of the dark between the stars, one that makes the silence of interstellar space something other than an absence. Perhaps something is out there, moving through the galaxy in the dark, warm inside, and alive. Let us imagine, carefully and without overclaiming, what life in a rogue planet's interior ocean might actually be like. Not the life as it might appear to an outside observer, because there are no outside observers and the ocean is sealed from all observation, but the life as it is, in itself, going about whatever processes constitute living in an environment that has never known anything outside itself. The first thing to understand is the scale of the available environment. The interior ocean of a rogue planet is not a small pond. If the ocean layer exists at depths between, say, 30 and 80 kilometers below the frozen surface, and if the planet is Earth-sized with a radius of about 6,000 kilometers, then the volume of the ocean is enormous. A global layer of water 50 kilometers deep, wrapped around the interior of the planet like a shell, covering an area comparable to the entire surface area of the Earth at that depth. The total volume of water in this ocean would be many times the volume of all of Earth's oceans combined. This is a vast environment, vast and completely enclosed, vast and completely dark, vast and heated from below and insulated from above, and divided internally by the slow circulation of warm water rising and cool water sinking, creating regions of different temperature and different chemical composition, different pressure and different mineral concentrations. Not uniform. Despite the absence of wind and waves and tides and seasons, the deep ocean of a rogue planet has structure, has gradients, has regions that are different from other regions. And it is in those gradients, in those regions of difference, that the most interesting chemistry happens. Think about what a hydrothermal vent on the floor of this ocean would look like. The rock at the base of the ocean is warm, heated from the deep interior. In some places, it is cracked. Water percolates down through the cracks, is heated by contact with the hot rock, dissolves minerals from the rock as it heats, and then rises back up through other cracks as hot mineral-laden fluid. Where this fluid emerges into the cooler ocean water above, there is a gradient, a sharp interface between hot and cool, between mineral-rich and mineral-poor, between the chemistry of the deep rock and the chemistry of the open ocean. At that interface, chemical reactions happen that would not happen elsewhere. Hydrogen sulfide from the vent fluid encounters sulfate in the ocean water, and the reaction releases energy. Hydrogen from serpentinization reactions, where water reacts with iron-bearing minerals, dissolves into the vent fluid and rises to the interface, where it can be oxidized by other compounds in the ocean water. These are not violent reactions. They are slow, mediated by the surfaces of mineral grains, proceeding at rates that are measured in years or decades or centuries. But they release energy, and energy drives chemistry, and chemistry, given enough time and the right conditions, has a way of producing complexity. On Earth, the earliest life almost certainly arose at environments exactly like this. The interface between hot mineral-rich water and cooler ocean water, at hydrothermal vents either on the ocean floor or in the porous rock that underlies the ocean. The chemistry of life, the particular way that carbon and hydrogen and oxygen and nitrogen and sulfur are assembled into the molecules of metabolism and heredity, reflects the chemistry of these vent environments. Life on Earth carries in its biochemistry the chemical signature of its origin at a mineral-water interface in the dark. If life arose in the rogue planet's ocean, it would begin at similar interfaces. The early chemistry would be the same kind of chemistry. Carbon chemistry in water, driven by the energy gradients of the vent environment, building up complexity one reaction at a time, one molecule at a time. The early organisms, if we can call them that, would be the simplest possible things. Molecular systems capable of copying themselves. Systems that could use the chemical energy of the vent environment to maintain their own organization. Systems that could evolve, changing their chemistry in response to the selection pressures of the environment. From those earliest beginnings, what might evolution produce over billions of years of isolation? The honest answer is that we genuinely do not know. Evolution is driven by the selection pressures of the environment, and the environment of a rogue planet's interior ocean is profoundly different from the environment of Earth's surface. There is no sunlight, so there is no selective pressure toward developing photosynthesis or light-sensitive pigments or eyes. There is no surface, so there is no selective pressure toward locomotion in a gravitational field, toward structures that support a body against gravity, toward behaviors that involve moving from one place to another in any directed way. What selective pressures would there be? The chemistry of the ocean, the availability of different molecules in different regions, the chemical gradients around the hydrothermal vents, The temperature differences between deep and shallow regions would all create selective pressures. Organisms that could move toward or away from particular chemical concentrations would have an advantage. Organisms that could tolerate the high pressure and high temperature near the vents would be able to exploit the richest energy sources. Organisms that could use a wider range of chemical reactions to generate energy would be more robust than those dependent on a narrow chemical niche. Over billions of years, these pressures might produce something. Not necessarily something large or complex in the way Earth life became complex, because the drivers of complexity on Earth were partly the rich and variable surface environment, the competition for sunlight, the co-evolutionary arms races between predators and prey in an open and highly variable world. The rogue planet's ocean is stable and enclosed. The selection pressures are gentler, more constant, less arms race-like. The result might be organisms that are exquisitely adapted to a very stable chemical environment, specialists in the chemistry of one particular vent or one particular chemical gradient. There is another possibility that is worth considering. The rogue planet's ocean has been in contact with its rocky floor for billions of years. The rock has been dissolving slowly, releasing minerals, releasing organic molecules that form during the geological processing of the deep rock, releasing the complex organic chemistry that builds up in rocks over geological time. If the rock itself contains prebiotic organic molecules, as meteorites do, as the interstellar medium does, then the ocean over billions of years has been receiving a slow delivery of complex organic precursors from the dissolving rock. The ocean is not just water and minerals. It is also, potentially, a slowly enriched soup of organic precursors, building up complexity over geological time, approaching the threshold of biological complexity from below. Whether that threshold is ever crossed depends on the specific chemistry and on the fundamental question of how probable the origin of life is. But the materials are there, the time is there, the energy gradients are there. And something else is there that is easy to overlook. The rock itself. The interface between the rock and the water is not just a chemical surface. It is a physical and geometrical environment. The pores and channels in the rock, at scales of micrometers and smaller, create confined spaces where molecules are concentrated, where diffusion is slow enough that reactions have time to proceed, where the mineral surfaces can act as catalysts. These confined pore spaces in the deep rock are, in many theories of the origin of life, essential. They provide the compartmentalization that allows chemistry to become cellular, the physical enclosure that allows the first self-replicating systems to maintain their organization. The deep rock of the rogue planet is full of such pore spaces. Billions of years of water-rock interaction has shaped the rock into an extraordinarily complex geometry of channels and chambers and surfaces. If life began in the pore spaces of the deep rock rather than in the open ocean, it might be life of a kind that has no analog on Earth at all. Not cellular life as we know it, but life embedded in the rock, using the mineral surfaces as part of its structure, living at the interface between the liquid and the solid in a way that blurs the boundary between geological and biological. This is not as strange as it sounds. On Earth, there are microorganisms that live deep in rock, in the tiny water-filled pores at depths of kilometers, where they survive on extremely slow metabolisms, dividing perhaps once every 1,000 years, maintained by the chemical energy available in the reactions between the rock and the water. These deep biosphere organisms are so slow and so minimal that for a long time we did not know they existed. They are the life of the surface, not the life of the open ocean. They are the life of the deep rock, and they have been there for billions of years. On a rogue planet, this kind of deep rock life might be the only kind of life there is. Not the rich surface ecosystems that exist on Earth, but the sparse, slow, ancient life of the deep interior. Organisms measured in micrometers, dividing on geological timescales, metabolizing at rates that would seem not like life, but like very slow chemistry to any observer impatient enough to require visible activity. But real, genuinely real, using chemical energy, maintaining organization against entropy, reproducing, however slowly, evolving, however gradually. Real life in the deep, dark interior of a world that has no sky, no sun, no surface, no season, no external reference point of any kind. Life that has never known anything else. Life that does not know it is isolated, because it has no concept of not being isolated. Life that is, in its own terms, entirely at home in the only environment it has ever known. The deep, warm dark of a frozen world drifting through the galaxy in silence. And perhaps, in the deepest and most literal sense, that is what it means to be at home. Not to be in a place that is familiar or comfortable by external standards, but to be exactly fitted to where you are, to be shaped by your environment into something that belongs there, that is sustained by it, that returns something to it by being alive within it. Life on a rogue planet would be the most deeply at home life in the universe. It would have nowhere else to be, no other world to reach, no sky to look at, no universe to wonder about. Just the warm, dark water, just the rock, just the slow chemistry, just the ancient, patient, isolated, quietly extraordinary fact of being alive. There is a philosophical question embedded in everything we have been describing, and it is time to bring it forward into the light. Not to answer it, because it does not have a clean answer, but to sit with it, to let it settle into the mind the way a stone settles into still water, slowly, with concentric rings of implication spreading outward from the point of impact. The question is this: what does it mean to move without a destination? We are accustomed, as creatures who navigate and plan and intend, to thinking of movement as purposeful. When we move towards something, toward a place we want to be, toward a person we want to see, toward a goal we have set for ourselves. Even when we take a walk without a specific destination, even when we wander, we carry within us a sense of agency, a sense that we could stop, that we could turn, that we are choosing to continue. The movement feels ours. It feels like something we are doing, not something that is simply happening to us. The rogue planet moves in a completely different way. It has no intention. It has no agency. It is not choosing its direction or its speed. It is simply following the laws of physics, moving in whatever direction its velocity carries it, modified by the gravitational field of the galaxy. And the direction it is moving has no particular significance. It is not moving toward anything. It is not moving away from anything, not deliberately, not anymore. The solar system it came from is far behind it, but it is not fleeing that solar system. It is just moving, the way a ball rolls when it has been given a push, the way a river flows when the terrain tilts in one direction. Movement that is not purposeful, movement that is not going anywhere. And yet it continues. Billions of years of movement that is not going anywhere. Billions of years of motion that has no goal, no narrative arc, no beginning that implies a particular kind of ending, no journey in any story sense of the word. Just the physics, just the velocity, just the galaxy's slow gravitational tug shaping the path into a long curve that is itself part of a larger orbit that takes 200 million years to complete. For us, this kind of movement is difficult to fully inhabit in the imagination. We have such a deep instinct that movement implies direction, implies purpose, implies meaning, that the idea of movement without any of these things feels almost like a contradiction. If it is not going anywhere, is it really moving? If the motion has no goal, does it have any significance? But consider this. The rogue planet's movement is not meaningless. It is just meaning of a different kind from the kind we're used to. It is the meaning of persistence rather than the meaning of purpose. The meaning of continuation rather than the meaning of arrival. It continues to exist in a universe that is cold and dark and ancient. It continues to carry its ocean, its frozen surface, its chemical archives, its tidal scars. It continues to sweep through the interstellar medium, accumulating its molecular diary. It continues to orbit the galactic center in its long, slow arc. All of this continuation is something. It is not nothing. The fact that the planet is still here, still moving, still maintaining its internal heat, still carrying its ocean, after billions of years of what we might be tempted to call aimless wandering, is itself a kind of achievement. Not an intentional achievement. Not an achievement in the human sense of having worked towards something and arrived there, but an achievement in the physical sense of having maintained a particular organized state of matter against the entropy that would otherwise have dispersed it. A rogue planet is a structure, a complex, organized, internally differentiated structure. It has layers. It has chemistry. It has temperature gradients. It has an ocean and a frozen crust and a warm interior and a rocky mantle and an iron core. All of these components are in relationship with each other. All of these relationships have been maintained over billions of years. The planet has not dissolved into a diffuse cloud of atoms. It has not collapsed. It has not come apart. It has remained what it is, a world, moving through the universe and remaining a world. That is movement without destination, but it is not movement without meaning. There is another way to think about this. The question of whether movement requires a destination to be meaningful might itself be a question worth interrogating. We assume that direction implies purpose because in human life, direction usually does imply purpose. We are goal-directed creatures. Our nervous systems evolved to navigate toward food and away from predators. Our cultures evolved to organize effort toward shared objectives. Our sense of meaning is woven through with the narrative structure of goals and their achievement. But this is our particular way of being in the universe. It is not the universe's way. The universe does not have goals. It does not move toward anything. Its processes, the expansion of space, the formation of stars, the evolution of galaxies, the slow decay of radioactive elements, none of these are directed toward an outcome in any meaningful sense. They are simply processes that proceed according to the laws of physics. They continue because the laws permit them to continue. They have no destination because destinations are a concept that belongs to navigating creatures, not to physical processes. And yet we find the universe beautiful. We find it interesting. We find it meaningful in a deep and difficult to articulate way. The expansion of the universe is not going somewhere, but it is extraordinary. The formation of a star is not purposeful, but it is magnificent. The evolution of life on Earth was not directed toward any goal, but it produced us, and we find ourselves worth being. The rogue planet's movement without destination is, in this light, not a deficit. It is simply the way the universe moves when there are no navigating creatures to impose their goal-directedness onto it. It is pure physics, pure continuation, pure persistence in the absence of any reason to stop. There is something quieting about this perspective. Because we spend much of our lives anxious about direction, about whether we are going the right way, about whether our movement is purposeful enough, productive enough, sufficiently aimed at something worthwhile. We judge our lives by their trajectories, by whether we are advancing or retreating, achieving or failing. And sometimes that judgment is useful, and sometimes it is exhausting, and sometimes it misses something important about what it means to simply be here, simply continue, simply persist from one moment to the next. The rogue planet does not judge its trajectory. It does not evaluate whether its galactic orbit is taking it somewhere interesting. It does not worry about whether its billions of years of motion have been well spent. It simply continues. It carries its warmth. It keeps its ocean. It sweeps through the interstellar medium and accumulates its chemical archive and orbits the galactic center in its slow, vast arc. And all of that continuation, all of that persistence, all of that movement without destination is not nothing. It is the quiet, unassuming, completely reliable fact of a world that continues to be a world that has not required any external purpose to justify its continued existence. A world that persists because the physics permits it, and that is enough. Movement without destination. It sounds like a description of being lost, but perhaps, in the deepest sense, it is a description of being exactly where you are. Not because you chose to be here, not because you are moving towards something else, but because you are here, now, and you are continuing, and the continuation itself is the whole of the story. Not a tragedy, not a failure, not even a question that requires an answer. Just a world, moving through the dark, carrying everything it is, going nowhere in particular, persisting. There is a kind of peace in that, if we can find it. A kind of peace that does not require arrival, does not require destination, does not require purpose in the human sense. A peace that comes from simply accepting the continuation. From understanding that being in motion is not the same as being lost. That going nowhere in particular can still be going somewhere. That the act of persisting, of carrying one's warmth through the cold and one's ocean through the dark, is itself a form of meaning that requires no destination to justify it. The rogue planet knows this in the only way a planet can know anything. By simply doing it, by continuing, by moving, by being still warm inside the dark. We have been circling around the most personal dimension of the rogue planet's existence throughout this entire journey, and now it is time to face it directly. The dimension of isolation, the fact of being alone in a way that has no human equivalent, in a way that exceeds anything our language was built to describe, in a way that is so absolute and so vast that even the word alone begins to feel inadequate. The rogue planet is isolated in a universe that is infinite, or very nearly infinite. In a universe that is, in every direction, so large that the distance to the nearest object of any significance is measured in light years, and the distances to the structures of the cosmic web are measured in millions and billions of light years. It is isolated in a universe that contains more galaxies than there are grains of sand on every beach of every ocean of the Earth, each galaxy containing hundreds of billions of stars, each star potentially with its own family of worlds. And yet none of that abundance touches it. None of that richness is available to it. It moves through the interstellar medium, and the interstellar medium is the thinnest conceivable presence, atoms spaced meters apart on average, not a community of any kind, not company in any sense that means anything. The nearest star might be a light year away. The nearest solar system with planets might be several light years away. The nearest object with any possibility of complexity might be dozens of light years away. A light year is approximately 10 trillion kilometers. If you drove at highway speed, it would take about 10 million years to travel 1 light year. The nearest star to our solar system is 4 light years away. The rogue planet, in its billions of years of travel, passes near perhaps 1 star per few 100 million years. Brief encounters, lasting astronomically speaking for eye blinks, and then the star recedes and the dark returns. The isolation is not merely spatial, it is temporal. The rogue planet has been isolated for longer than the Earth has existed. It was ejected from its home solar system, and from that moment forward it has been alone. Not alone the way a person is alone in a room, which is alone in the most superficial sense, with walls and floors, and a building, and a city, and a world of people just outside. Not alone the way a person is alone on a mountain, which is alone with the sky and the rock and the vast impersonal beauty of high altitude, but with the knowledge of the valley below. Alone the way nothing in human experience is alone. Alone with the galaxy as its only companion, and the galaxy is not a companion. The galaxy is a gravitational environment, a distribution of mass that shapes the rogue planet's orbit the way a river bed shapes water. The galaxy does not know the rogue planet is there. The galaxy does not offer anything. The galaxy is simply the context within which the rogue planet moves, a context so large and so indifferent that it cannot be thought of as company. And yet,